Find the shape that lets your body feel heavy and still. There is no wrong way to do this. You might be on your back or curled on your side or somewhere in between. Wherever you are, let the surface beneath you hold your full weight now. Let your shoulders drop away from your ears. Let your jaw unclench. Let your hands fall open if they want to. The story is about to begin, but you do not need to hold on to any of it. You do not need to remember a single word. This is a story told softly in the dark, and its only job is to keep you company while you drift. We are going to walk together through one long, continuous story. It is the story of everything we know, from the very first moment we can speak about, all the way to this quiet room, right now, with you in it. It is a story that spans an almost unthinkable stretch of time. When we measure it out, the number sounds too large to feel real. Something like 13,800,000,000 years. That is 13,000 million years, with another 800 million added on. It is the kind of number that slides right past understanding, and that is perfectly fine. We are not here to do math. We are not here to hold big numbers in our heads. We are here to let the story wash over us slowly, like water, like breath, like the soft hum of a distant road at night. Because the story is so long, we are going to take our time with it. We are going to move through it at the pace of a slow, steady exhale. There will be no rush. There will be no test at the end. If your mind drifts away from the words, that is not a mistake. That is the point. Let the words become a texture in the background, something your mind can rest on, or drift away from, and then come back to, finding it still there, still moving gently forward. You can dip in and out, and the story will still be whole. It will still be waiting for you, unhurried, unchanged. I want to tell you, right at the start, something that might help you relax into this. Not every part of this story is known. There are pieces we do not have. There are questions we cannot yet answer, and some we may never answer. The very beginning, the moment before the first moment, is one of those open questions. What happened before the universe began is not something anyone can tell you with certainty. It may not even be the right question to ask, and that unknown, that gentle mystery, is not something we need to paper over or fix. It is part of the story too. It is part of the calm. The not knowing sits at the edges of everything we do know, like a soft, dark frame around a painting. We will name it when we come to it. We will pause and acknowledge it, and then we will move on from it, just as gently, back into the light of what we do understand. So settle in now, as deeply as you can. You might take one more slow breath, in through the nose, and then let it go out through the mouth, long and low, as if you were fogging a cold window. Feel the small drop that happens inside your chest when the breath leaves you. That drop is the feeling we are looking for. That is the feeling of letting go of the day, letting go of the need to track anything, to plan anything, to solve anything. For the next little while, there is nothing to solve. There is only this story, moving at its own slow pace, and your mind floating somewhere nearby, resting. The story begins in a place we cannot really picture. It begins with everything, all the matter, all the energy, all the space that would ever exist, compressed into something so hot and so dense and so small that our usual words break against it. It was not an explosion in space, the way a firework explodes in the sky. It was an expansion of space itself. Space itself began to stretch and grow, and in the very first tiny slivers of a second, things happened that we are still working to understand. We will get to that soon, but for now, just hold that single, simple image in your mind, as if you were looking at it through closed eyelids. A beginning, a stretching, a cooling, a long, slow unfolding that has not stopped, even now, even tonight, as you lie here. The story will move from that first moment into a time of pure, formless energy, too hot for anything we would recognize as matter. Then it will cool, slowly, over hundreds of thousands of years, until the first simple atoms can form. Hydrogen, mostly, a little helium. The simplest building blocks, Then comes a long, quiet stretch we call the Dark Ages, a time when there were no stars yet, no light, just vast clouds of these simple atoms, drifting and gathering, pulled ever so gently by gravity. It was dark, and it was silent, and it lasted for a few 100 million years. That is a long time to be dark, a long time to be still. And through all of that stillness, gravity was working, patient as breath, pulling the clouds together into denser and denser pockets. Then, in some of those pockets, the first stars flickered on. We will come to that. We will talk about how stars are born, how they live, how they make the heavier elements in their cores, and how they scatter those elements back into space when they die. We will talk about how our own sun was born, from a cloud of gas and dust that had been enriched by earlier generations of stars. How the Earth formed from the leftover disk of material swirling around that young sun. How, on that Earth, in its cooling oceans, life began. How that life grew and changed over billions of years, from single cells to the wide, branching tree of life we are a part of. And how, after all of that, we arrive here, at this moment, at this quiet room, with you in it, listening. It is a long story, but we are going to tell it slowly. We are going to let it breathe. Each part of the story will get its own space, its own time to settle in the air before we move on. We will not rush from one thing to the next. We will pause. We will repeat. We will circle back and restate things in slightly different words, not because you need to learn them, but because the repetition itself is soothing. A half-asleep mind does not need new information. It needs a familiar shape to follow, a soft path it can walk without having to pay close attention. So if you hear the same idea come around again, wrapped in new words, let that be a comfort. It means you do not have to rewind anything. You do not have to catch up. The story itself will carry you forward, even if you miss a piece, even if you fall asleep in the middle of a sentence. That is what it is for. Think of this story as a slow river, and you are floating on your back in it, looking up at a night sky. The current is carrying you. You do not need to paddle. You do not need to steer. You can close your eyes and still feel the movement beneath you. The words will keep coming, steady and even, and they will not demand anything from you. They will not ask you to be alert or to remember or to care. They will simply be there, a soft, continuous presence, like rain on the roof, like the hum of a fan in the corner of the room. We are going to start very soon now, at the very edge of what we can describe, the first fraction of a second. But before we even get there, we need to pause for just a moment at the boundary, at the thing we cannot describe, at the before, what came before the beginning. We will stand there, together, and acknowledge that the question itself may not have an answer. And that is not a failure of the story. That is part of its shape. Every story has an edge. Every map has a place where the known land ends and the blank space begins. We will honor that blank space. We will not fill it with guesses dressed up as facts. We will simply note it and then step gently over the threshold into what we do know, into the heat and the density and the stretching of space itself. So for now, just breathe. Just let the weight of your body sink a little deeper into the bed. Let the room be dark, or as dark as you can make it. Let the sounds of the house or the street outside become part of the texture, not distractions but simply part of the night. There is nowhere you need to be. There is nothing you need to do. The story is about to unfold, a long, slow ribbon of time, from the first instant to this one, and you are allowed to fall asleep at any point along the way. In fact, that is the hope, that somewhere between the first atoms and the first stars, or maybe between the formation of the earth and the first stirrings of life, your mind will simply let go and drift and not need to hear the rest. The story will still be here, continuing on without you, and that is a gentle thought, not a lonely one. 13,800,000,000 years. It is a number so large it feels abstract. So let us not hold it as a number. Let us hold it as a feeling instead. A feeling of immense patient time, a feeling of slow, steady unfolding, a feeling of processes moving at scales so far beyond a human lifetime that they become almost peaceful to contemplate. A star takes millions of years to form, a galaxy takes hundreds of millions. The universe itself has been expanding for almost 14 billion years, and it is still going, still stretching, still making room. Against that scale, our own small worries, the things that chased each other through your mind today, become very quiet. They are still real, but they are small. And small, in this context, is a relief. Small is a gift. Small means you can let them rest, just for now, and pick them up again in the morning if you need to. The story we are about to tell is the story of how that immense, patient time produced this moment. This exact configuration of atoms, this breath, this room, this quiet. It is not a story about meaning or purpose. It is simply a story about sequence. First this happened, then this. And if there is any wonder in it, it is the quiet wonder of noticing that you are here, at the end of this long chain of events, lying in the dark, listening to a voice. That is enough. That is more than enough. So let the day go. Let it peel away from you like a layer of clothing you no longer need. The conversation you replayed in your head, the task you did not finish, the thing you are supposed to remember tomorrow. None of it needs to be held right now. You can set it all down. The story will hold the space for you. It will fill the silence with something soft and steady, so your own thoughts do not have to rush in. And if they do rush in, if they do interrupt, that is all right too. Just notice them, and let them float away again, and come back to the sound of the words. The words will be here. They are not going anywhere. In a moment, we are going to step back to the very edge of what we know, to the question of what came before the beginning. We will stand there together, in the dark, looking at that question. We will not try to answer it. We will simply acknowledge it, and then we will turn, gently, toward the first moment we can describe, the first instant, the heat, the density, the stretching, the long, slow beginning of everything. That is where the story starts. But before that, there is the before, and the before is a mystery. And that mystery is our next soft step. So breathe and settle, and let the story carry you forward, at its own slow pace, into the dark. Here we are, at the edge, the very edge of the story, the place where the path of what we know simply stops, and beyond it lies a quiet, open question. We are standing at the threshold of the beginning, looking back, or trying to look back, into something we cannot see, and that is where we will stay for a little while. Not trying to solve it, not trying to guess, just standing here together, in the dark, acknowledging the mystery for what it is. The question seems simple enough. What happened before the universe began? It is a question that rises up in us almost automatically. Every story we have ever heard has a before. Before the hero set out on the journey, before the sun rose, before the first page was turned. So it feels natural to ask what came before the beginning of everything. But one of the first things we have to sit with, here at the edge, is the possibility that the question itself may not work the way we think it does. The word before relies on time. Before is a word that assumes there was a moment, and then a later moment, and then a still later moment. Before assumes a sequence, a clock ticking, one thing following another. But if time itself began with the universe, then there was no before. There was no earlier moment. There was no ticking clock, no sequence, no one thing following another. Time, in the way we experience it, may have simply started. The first moment of the universe may also have been the first moment of time. And if that is true, then asking what came before time began is like asking what is north of the North Pole. The question itself dissolves. It does not point to a mystery we cannot solve. It points to a concept that may have no meaning at all in that context. Now it is important to say this plainly, and to say it calmly. This is not something we are simplifying for the sake of the story. This is genuinely where the science stands. Among the people who study the universe for a living, the question of what came before the Big Bang is unresolved. It is not that they know the answer and are keeping it from us. It is not that the answer is too hard to explain. It is that we do not know. And more than that, we are not even sure the question is a valid one to ask. The laws of physics, as we understand them, break down at the very first instant. Our equations stop giving us clear answers. It is as if we are trying to read a book that begins mid-sentence, and the pages before that first sentence are not just blank. They may not exist at all. They may never have been written. There are ideas, of course. There are always ideas. Some thinkers have wondered if our universe emerged from something else, some earlier state, some deeper structure. Others have wondered if time itself is not as fundamental as we think, if it is something that emerges rather than something that simply is. There are models and proposals and mathematical frameworks, but none of them have been confirmed. None of them rise to the level of settled understanding. They are possibilities, floating in the dark, and we can look at them the way we look at faint stars on a cloudy night. We can acknowledge them. We can note their presence, but we cannot draw them into sharp focus. Not yet. Maybe not ever. And this not knowing, this honest uncertainty, is not a problem to be fixed. It is not a gap that ruins the story. It is the frame around the story. It is the soft, dark edge that holds the picture. Every story has an edge. Every map has a place where the known land ends and the blank space begins. In old maps they used to write, "Here be dragons," at the edges. But there are no dragons here. There is just quiet. Just an honest admission that we have reached the limit of what we can say with confidence. And that limit is a peaceful place, if we let it be. It does not need to be filled with noise or speculation or guesses dressed up as facts. It can simply be what it is. An edge, a boundary, a place where we stop and take a breath before stepping into what we do know. So let us stand here for a moment longer, at this boundary, and let the feeling of it settle in. The feeling of not knowing, the feeling of reaching the end of the path and finding not a wall but a wide, open field of quiet. It is a humbling feeling. It reminds us that we are small, and that our understanding is partial, and that the universe does not owe us answers to every question we can think to ask. And that is not a cold or lonely thought. It is a warm one, in its own way. It means we are part of something larger than our ability to comprehend it. It means there will always be more. There will always be mystery. There will always be a soft, dark edge beyond which we cannot see. Now, having acknowledged that edge, having stood at it and let it be what it is, we can turn around. We can face the other direction, the direction of the story we can tell, because the boundary is not the whole story. It is only the starting point. From here, we can step forward into the first moment that our physics can describe with some confidence. And that moment is not a vague, hand-waving idea. It is a precise, well-tested understanding. We can trace the history of the universe back to an astonishingly early time, a tiny fraction of a second. A sliver so thin that our usual words for time, seconds, minutes, hours, are far too large and clumsy to hold it. We need new words. We need new ways of thinking, and we will get there. But for now, just know this. The story we are about to step into begins in a state that is almost impossible to picture. Everything that would ever become the universe, all the matter, all the energy, all the space, was compressed into something so hot and so dense and so small that our everyday imaginations cannot hold it. It was not a thing sitting in an empty room. There was no room. There was no empty space around it. Space itself was part of what was compressed. Space itself was about to begin stretching. And then it did begin. The stretching started. The expansion started. Not an explosion, in the sense of something blowing up into an existing space. That is a common picture, but it is not the right one. There was no center to the explosion. There was no outside for the explosion to expand into. It was space itself that expanded. Every point in the universe began moving away from every other point. The distance between things grew. It was not that matter was flying apart through space. It was that space itself was growing and carrying the matter along with it. Like dots on the surface of a balloon being inflated. The dots do not move across the surface. The surface itself stretches, and the dots get farther apart. That is closer to the right picture, though no picture is perfect. The universe was not a balloon expanding into a room. There was no room. There was no outside. As far as we can tell, the universe is all there is, and it was simply getting larger, stretching itself, making more room where there had been less room before. This expansion, this stretching of space, is the thing we call the Big Bang. The name is a little misleading. It sounds loud, it sounds sudden, but the Big Bang was not a bang in the way we think of bangs. It was not a noise. There was no air for sound to travel through. There was no one there to hear it, even if there had been. It was a vast, silent stretching, a cooling, an unfolding, and it has never stopped. The universe is still expanding today. The stretching is still happening. We will talk about that much later, when we come to the part of the story where we are now. But the key thing to hold on to as we step forward from the edge of the unknown into the first known moment is this. The universe began in a state of almost unimaginable heat and density and smallness, and then it began to expand and cool. And that expansion and cooling is the story we are going to tell. It is the spine of the whole narrative. From that first moment to this one, the universe has been expanding and cooling, making room, making space for structure to form, making space for atoms, making space for stars, making space for galaxies, making space for planets, making space for you lying here in the dark, listening. So let the mystery of the before settle behind us now. We have acknowledged it. We have given it its due. We have not tried to solve it, because it cannot be solved, not yet, and maybe not ever, and that is all right. That is part of the calm. The not knowing is not a wound. It is a door that opens onto a larger sense of peace. We do not need to understand everything. We do not need to have every answer. We can simply be here, in the part of the story we do know, and let the rest be dark and quiet and still. Now we step forward, into the heat, into the density, into the first tiny fraction of a second. That is where the next part of the story begins. The first instant, the moment when everything we can describe was already in motion, already expanding, already cooling. We will go there now. We will walk into that heat together, slowly, and we will describe it as carefully and as gently as we can. There will be no rush. The universe itself took its time, over billions and billions of years, to get from that first instant to this quiet room. And we will take our time too. We will let the words come slowly. We will let the images form and dissolve. We will rest in the spaces between them. So breathe. Let the dark hold you. The story is moving forward now, at its own slow pace, into the first light, into the first moment, into the beginning of everything we know. We are stepping into the heat now, into the very first moment that our understanding can reach. It is a moment so far back, so close to the edge of the unknown, that our everyday words struggle to hold it. But we will try. We will use simple words, and we will go slowly, and we will let the images form, as best they can, in the quiet dark behind your closed eyes. The universe, at this first instant we can describe, was almost unimaginably hot. Not hot like a summer day, not hot like an oven, not even hot like the center of a star. Hotter than all of those things put together, by orders of magnitude that the human mind cannot really grasp. It was a heat so intense that matter as we know it could not exist. There were no atoms, there were no molecules, there were not even the smaller pieces that atoms are made of, the protons and neutrons that sit at the center of every atom. Those had not yet come into being. The heat was simply too great for anything to hold together. It was a smooth, dense, searing state, where energy and matter were essentially the same thing, a single writhing field of pure potential, too hot to form any structure at all. and this state was not spread out across a vast sky. It was compressed into a space that was, by any measure we can relate to, tiny. The entire universe, everything that would ever become galaxies and stars and planets and you, was packed into a volume smaller than an atom, smaller than the smallest thing you can picture, all of it, all of space, all of the raw material for everything that would ever exist, crammed into a speck so small that if you held your thumb and forefinger a hair's breadth apart, that gap would be a universe too large to compare. The density was as extreme as the heat. The two go together, hot and dense and hot. A single point of searing compacted everything. And then, right from this first instant, the universe began to do the thing it has been doing ever since. It began to expand. It began to stretch. Space itself began to grow. And as space grew, as the distance between points increased, two things happened that are deeply linked. The universe began to cool, and it began to become less dense, cooling and thinning, stretching and cooling. This is the same principle that governs a can of compressed air. When you spray it, the gas expands rapidly, and the can feels cold in your hand. Expansion brings cooling. On a scale vastly larger and far more gentle at first, the expanding universe began to cool from its initial state of impossible heat. This expansion, this stretching of space itself, is what we call the Big Bang. The name is worth pausing on, because it can be misleading if we are not careful. The words Big Bang suggest a loud noise, a sudden explosion, a violent blast at a particular point. But that is not what the science describes. The Big Bang was not an explosion in space. It was an expansion of space. There was no center to it. There was no single location where it happened. It happened everywhere at once, because everywhere was the same place. The expansion carried all points away from all other points. It was not matter flying apart through a pre-existing emptiness. It was emptiness itself, space itself, being created and stretched between the particles of matter. The space between things grew. The space between every point and every other point simply became larger, and it did so silently. There was no air to carry sound. There was no one there to hear it, even if sound could travel. It was a vast, silent stretching, an unfolding, a cooling. Now, within this very first tiny fraction of a second, something else may have happened. Something we are still working to confirm. The idea is called cosmic inflation, and the word inflation here does not mean rising prices or balloons in a party sense. It refers to a proposed period of extremely rapid stretching, unimaginably rapid, a burst of expansion that happened in a sliver of a second, far faster than the expansion that followed it. In this proposed burst, the universe expanded by a staggering amount in an almost unthinkably short time. It grew and grew, doubling and doubling again, smoothing itself out, before settling into the more gradual expansion we observe today. This idea of inflation is a leading one. It helps explain why the universe looks so smooth and even in all directions, why the temperature of the deep sky is so similar everywhere we look. But it is important to say, calmly and plainly, that inflation is still an idea being tested. It is not yet settled in the way other parts of the story are settled. The evidence is suggestive, the mathematical models are compelling, but the final confirmation is not yet in. And that is all right. That is part of the story too. We can hold this idea gently, as a strong possibility, while also naming the uncertainty that still surrounds it. The not knowing is not a flaw, it is the honest shape of the frontier. But whether inflation happened in exactly that way or not, the broader picture of the first instant is on much firmer ground. The universe began in a state of extreme heat and extreme density. It began to expand and cool. And in that expansion, the stage was set for everything that would follow. That is the core of it. That is the foundation on which the rest of the story rests. Now, there is another question that often rises up when we try to picture this. If the universe is expanding, what is it expanding into? That is a very natural question. Our minds are used to things expanding into a container. A balloon expands into the air around it. A puddle of water spreads across a floor, so it feels like there must be some larger space, some outside, that the universe is growing into. But as far as we can tell, there is no outside, there is no container. The universe is all of space and all of time. It is not expanding into anything. It is simply expanding. The space within it is growing. The distances between things are increasing, but there is no edge, no boundary, no wall that the universe is pushing against, and there is no empty void beyond the universe that it is filling. The universe is the whole. It contains all the space there is. When it expands, it is not claiming new territory, it is simply stretching the territory that already exists. That is a hard picture to hold in the mind. It is hard because our minds evolved to understand medium-sized things moving through other medium-sized things. We are not built to picture the behavior of all of space and time, and that is perfectly fine. We do not need to picture it clearly. We just need to hold the words gently and let them settle, without forcing them into a sharp image. The universe is expanding. There is no outside. That is enough. So let us return to the heat. In that first moment, the temperature was so high that none of the particles we are made of could exist. The very idea of a particle, a small, solid speck of something, was not yet meaningful. The universe was a kind of fierce, uniform soup of energy, but it was cooling. With every tiny fraction of a second, as the stretching continued, the temperature dropped, and as it dropped, the universe crossed thresholds. At certain temperatures, certain things became possible that had not been possible before. This is a pattern we will see again and again throughout the story. Cooling allows structure. Heat is the enemy of form. When things are too hot, they fly apart. They cannot stick together. They cannot bind into larger wholes. Only as the temperature falls do new kinds of order become possible. The story of the universe is, in a very deep sense, a story of cooling. A story of thresholds crossed, one by one, as the temperature slowly dropped. The first threshold, the one we are approaching now, is the threshold where energy begins to condense into the smallest building blocks of matter, fundamental particles, the tiniest specks that cannot be broken down further. Things like quarks and electrons. We will talk about them soon, but for now, just know that, in this first instant, they were on the verge of appearing. The universe was preparing the ground. The heat was still too great for them to exist as separate, stable entities, but the cooling was underway. The stretching was doing its slow, steady work, and soon, in the very next few fractions of a second, the first particles would flicker into being, swimming freely in the still ferocious heat. The universe of pure energy was about to become a universe of moving, colliding, interacting specks. A new phase, a new chapter, but we are not quite there yet. We are still here, in the first instant, in the heat, in the density, in the silent, stretching dark. Take a breath. Let the image soften. You do not need to picture this perfectly. You do not need to understand it fully. The words are enough. The rhythm is enough. The story is moving at its own pace, and you are simply floating alongside it. The heat, the density, the stretching, the cooling. Those 4 words carry the whole first chapter. The heat, the density, the stretching, the cooling. Let them repeat in your mind like a slow, quiet mantra while the rest of the story gets ready to unfold. We are at the beginning, the very beginning, and there is so much time ahead of us, so much time. The universe is still very young now. We are deep inside the first tiny fraction of a second. The heat is still almost beyond anything we can put into words. The density is still almost beyond anything we can picture. And yet, the cooling has already begun. The stretching has already begun. And because of that cooling, the universe is about to cross a threshold. It is about to move from a state of pure, formless energy into a state where the first small building blocks of matter can appear. Not atoms yet, not even the cores of atoms, but the tiniest specks that will one day, much later, come together to build those things. We are entering the time when the universe becomes a place of moving particles, a vast, hot sea of them, swimming freely through the still expanding space. To understand this phase, we need to hold one simple idea in our minds. Heat is the enemy of structure. When things are hot enough, they cannot stick together. The particles move too fast, they collide too hard. Anytime two of them meet, the force of the collision tears them apart again before they can settle into any kind of partnership. It is only as the temperature falls that particles can begin to stay near each other, to bind, to form larger wholes. So the story we are telling now is a story of cooling, a story of the temperature dropping, degree by degree, through thresholds that allow new kinds of order to emerge. This is the deep rhythm of the whole cosmic story. Cooling and structure, stretching and cooling. As space grows, the heat spreads out, becomes thinner, becomes gentler. And in that growing gentleness, new things become possible. In the very first slivers of a second, the universe was still too hot for any of the particles we know to exist as separate, stable things. What we mean by a particle, in the simplest terms, is a tiny, distinct speck of something, a small, local bundle of energy and mass that can move through space and interact with other such bundles. But in that earliest moment, the distinction between one speck and another was not yet clear. The universe was a kind of smooth, searing field where everything was blended together. Energy was not yet sorted into the neat categories we use today. There was no such thing as an electron or a quark or a photon as separate identifiable entities. The whole was a single, writhing, superheated something, too energetic to be broken into pieces that could hold their shape. But as the universe expanded and cooled, the first particles began to condense out of that field, like tiny droplets of water forming from a cloud of steam. Not suddenly, not all at once, but gradually, as the temperature dropped past a certain point, the building blocks of matter flickered into being. The smallest ones, the fundamental ones, the ones that cannot be broken down into anything smaller. One group of these fundamental particles is called quarks. Quarks are among the tiniest specks of matter we know of. They are so small that we do not experience them directly in everyday life. They are tucked away inside larger particles, bound together so tightly that we never see a quark on its own. But in this early moment, in the fierce heat of the young universe, quarks were not yet bound into anything. They were moving freely, independently, through the hot, dense soup. They were swimming, colliding, bouncing, a vast, restless population of the smallest bits of matter, filling all of space. Alongside the quarks, another type of particle was also appearing. These are called electrons. Electrons are much lighter than quarks. They are the particles that, much later in the story, will orbit around the outsides of atoms. They are the particles that carry electric charge in wires, that flow through circuits, that make up the outer layers of all the atoms in your body. In the everyday world, electrons are always found attached to atoms, circling the dense central cores. But here, in the early universe, it was far too hot for atoms to exist. So electrons, like quarks, were moving freely. They were not bound to anything. They were just swimming, along with everything else, in the hot, dense sea. And there were other particles too. Particles of light, which are called photons. Particles that carry forces, which act like messengers between the matter particles, telling them how to push and pull on each other. There were neutrinos, tiny ghostly particles that barely interact with anything at all. The whole universe was a thick, bright, churning mixture of all these things, quarks, electrons, photons, and more, all of them moving at tremendous speeds, all of them colliding and ricocheting and flying apart again. It was a state of matter so hot and so energetic that no two particles could stay bound together for long. The moment a quark found itself near another quark, a photon would slam into them, or the heat of the collision would simply knock them apart. Nothing could stick. nothing could build. This state of matter, where particles are so hot that they cannot bind into atoms or even into the cores of atoms, has a name. It is called a plasma. In everyday life, we do not encounter plasma very often, though it is actually the most common state of ordinary matter in the universe. The sun is made of plasma. The stars are made of plasma. Lightning is a thin thread of plasma cutting through the air. A plasma is a gas whose particles have been heated so fiercely that they have been ripped apart from each other. Electrons are torn away from their atoms and set free. The whole thing becomes a kind of electrically charged soup, a gas of loose, fast-moving specks that no longer form whole, neutral atoms. The early universe, in this first fraction of a second, was a plasma in its most extreme form. Not just electrons ripped from atoms, because there were no atoms yet, but even the smaller pieces, the quarks, were ripped apart from each other. It was a plasma of the most fundamental parts. A quark gluon plasma, to give it its formal name. But we do not need to hold on to the formal name. The simple idea is enough. The universe was a hot, dense soup of the smallest bits of matter, all moving freely, all swimming independently, too hot to combine into anything larger. And all the while the expansion continued. The stretching of space did not pause. With every tiny fraction of a second, the universe grew a little larger, a little less dense, a little cooler. The particles, still swimming and colliding, found themselves with a little more room. The collisions became slightly less violent. The temperature dropped step by tiny step. The universe was preparing to cross the next threshold, the one where quarks could finally hold hands with each other, the one where they could bind together into the next level of structure, protons and neutrons, the cores of atoms. We will come to that soon, but for now, we are still here, in the universe of pure energy and free particles, a universe without atoms, a universe without chemistry, a universe without anything solid, anything liquid, anything that could cast a shadow or reflect light. Just a smooth, bright, incredibly hot sea of the tiniest specks, filling all of space, expanding and cooling in the dark. Let the image rest in your mind, as soft and as loose as it needs to be. You do not need to picture the individual quarks. You do not need to track the electrons. You can simply imagine a great, warm, glowing mist, a fog of light and motion filling everything there is. A fog that is slowly thinning, a fog that is slowly cooling, a fog that, over time, will begin to clump and gather and build the structures we know. But that time is not yet. Right now, the fog is still formless, still too hot for form. And there is a kind of peace in that formlessness, a kind of rest. No sharp edges, no hard surfaces, just a smooth, continuous, slowly cooling sea of almost particles, drifting through the first second of the universe's long life, drifting and waiting and cooling, drifting and waiting and cooling. The heat is still immense, but it is less immense than it was a moment ago, and soon, very soon, the first real structures will begin to appear. The first protons and neutrons, the first tiny solid cores, the first stable specks that will survive to become the matter of our world. We are almost there. The universe is getting ready. The cooling is doing its slow, steady work, and we are drifting with it, through the heat, through the light, toward the next threshold, toward the first atoms that will ever form. The cooling continues, the stretching continues. And now we have reached a moment when the universe is about 1 second old. 1 full second. It may seem like a very short time, and in the scale of a human life it is, but measured against the frantic pace of the first few fractions of a second, a full second is an immense stretch. It is long enough for the temperature to have dropped significantly, long enough for the hot, formless fog we were drifting through to begin organizing itself into something new. The quarks, those tiny fundamental specks we spoke of earlier, are no longer moving completely freely. The cooling has brought the universe to a threshold where they can at last hold on to each other. They can bind together in small, stable groups. And when they do, they form the first real building blocks of the matter we know today. These groupings of quarks are called protons and neutrons. You may have heard those names before. Protons and neutrons are the particles that sit at the center of every atom. They are the dense, heavy cores around which electrons will eventually orbit. In the everyday world we live in, every atomic core, every nucleus, is made of protons and neutrons stuck tightly together. But here, in the 1-second-old universe, they have just appeared for the first time. The quarks, which had been swimming alone in the hot plasma, have finally cooled enough to come together in threes. Two types of quark, in different combinations, bind to form a proton or a neutron. A proton is made of 2 up quarks and 1 down quark. A neutron is made of 2 down quarks and 1 up quark. The names are not important for our story. What is important is the simple fact that small, stable specks of matter have now formed. The universe has its first solid pieces. It has moved from a featureless, searing soup of the very smallest bits into a place where those bits have begun to join hands and build something larger. This process, the very first joining of fundamental particles into larger, stable cores, is a deep moment in our story. It marks the beginning of structure, the beginning of matter as something that can have shape and size and identity. Protons and neutrons are still unimaginably small by human standards, but they are real, distinct, lasting objects. They can survive. They can persist through the continued expansion and cooling. They are the raw material out of which everything else will eventually be built. All the atoms in your body, all the atoms in the earth, all the atoms in every star and every planet began their existence as protons and neutrons formed in the first few seconds of the universe. The hydrogen in the water you drink, the oxygen in the air you breathe, the carbon that makes up the backbone of every living cell, all of it traces back to this quiet moment, about 1 second after the beginning, when quarks first bound together into protons and neutrons. Now, the universe at this point is still far too hot for whole atoms to exist. An atom is a much more complex thing than a bare proton or neutron. An atom requires electrons to be gently held in orbit around a central core, and the heat is still too fierce for that. Electrons are still flying around too fast. Photons, the particles of light, are still slamming into everything with too much energy. If a proton tried to capture an electron, the electron would be instantly knocked away by a passing photon. So we are not yet at the stage of atoms, but we have reached the stage of atomic cores. The universe is now filled with a hot, dense sea of free protons, free neutrons, free electrons, and photons. A slightly more organized soup than before, a soup with recognizable pieces in it. Protons, which carry a positive electric charge. Neutrons, which carry no charge at all. Electrons, which carry a negative charge. And photons, the carriers of light. All of them swimming together, colliding and interacting in the still expanding, still cooling cosmos. And because the universe has cooled enough for protons and neutrons to exist, another process can now begin. Some of these protons and neutrons can start to stick to each other. Not all of them, and not for very long at first. But occasionally, in the dense, warm soup, a proton and a neutron will come close enough to bind together. When they do, they form something new. A small cluster of 2 particles, a proton-neutron pair. This cluster is the core of a type of atom you may have heard of. It is the nucleus of deuterium, which is a heavier form of hydrogen. Ordinary hydrogen, the simplest atom there is, has a core made of just a single proton, all by itself. Deuterium, which is sometimes called heavy hydrogen, has a core made of 1 proton and 1 neutron bound together. This is the first step toward building anything more complex than a lone particle. A single proton is just a proton, but a proton and a neutron stuck together is the beginning of something larger. It is the first composite core, the first atomic nucleus that contains more than 1 piece. From here, the building continues. If another neutron binds to the deuterium core, you get a core with 1 proton and 2 neutrons. That is tritium, another form of hydrogen. And if, instead, another proton binds, you get a core with 2 protons and 1 neutron. That is a light form of helium. And if 2 protons and 2 neutrons come together, you get the most common form of helium, the familiar helium we use to fill balloons, the second lightest and second simplest element in the universe. This process of building up atomic cores by adding one particle at a time has a name. It is called nucleosynthesis. The word simply means the making of nuclei, the making of atomic cores. It is the first act of construction in the universe's long history, the first time that smaller pieces combine to form larger, more complex pieces. And it happened very quickly, in the first few minutes after the universe began. The conditions for this building were very specific. The universe had to be cool enough for protons and neutrons to stick together, but still hot and dense enough for them to actually find each other and collide. That window of time was brief. After about 3 minutes, the universe had expanded and cooled so much that the density was too low. The particles were too spread out. They could no longer find each other reliably enough to keep building. So the era of nucleosynthesis was short. A few intense minutes of construction, and then the window closed. And when it closed, the ratios were set. The universe had cooked up a specific mix of simple atomic cores, and that mix would remain largely unchanged for a very long time, until stars began to alter it. That mix was mostly hydrogen, the simplest possible core, a single proton, all by itself, with nothing else attached. Hydrogen was, and still is, the most abundant element in the universe. After hydrogen came helium. Helium cores, made of 2 protons and 2 neutrons, were the second most common product of this early cooking. Together, hydrogen and helium made up almost everything. Something like 3/4 of the ordinary matter in the universe was hydrogen, about 1/4 was helium, and only a tiny trace, a fraction of a fraction, was anything heavier. A little bit of lithium, the next element after helium, was formed. And essentially nothing beyond that. No carbon, no oxygen, no iron, no gold, no silver, no elements of the kind that make up rocks and oceans and living bodies. The early universe simply did not have the time or the conditions to build those heavier, more complex cores. For that, we would need stars. And stars were still a long, long way in the future. So after about 3 minutes, the era of building atomic cores was over. The universe continued to expand and cool. The protons, the neutrons, the electrons, and the newly formed cores all continued to swim in the hot plasma. They were still not whole atoms. The electrons were still unattached. The cores, what we call nuclei, were bare, positively charged, and constantly buffeted by photons. The universe remained a bright, thick, opaque fog. Light could not travel freely because it kept slamming into the free electrons. A photon would try to move in a straight line, but it would immediately hit an electron and scatter in a random direction. Then it would hit another electron and scatter again. The light was trapped, bouncing around in a kind of cosmic pinball game, unable to go anywhere in a straight line. If you had been able to stand in that early universe, and of course you could not have, there was no place to stand, no ground, no air. But if you could have, you would not have been able to see anything. The universe was a dense, glowing fog, bright but completely opaque, like being inside a cloud or a thick mist lit from all directions. No shapes, no shadows. No clear line of sight, just a diffuse, even glow in every direction. This state of affairs lasted for a very long time by human standards, about 380,000 years. 380,000 years of the universe being a hot, opaque, glowing fog of free electrons, bare atomic cores, and trapped light. During all that time, the universe was expanding and cooling. The temperature was dropping, slowly but steadily. And then, at around the 380,000-year mark, the temperature finally dropped past a critical threshold. It became cool enough for the electrons and the bare atomic cores to join together. The electric attraction between the positively charged cores and the negatively charged electrons, which had always been there, was no longer overwhelmed by the heat of the photons. The photons had cooled to the point where they no longer carried enough energy to knock the electrons away. So the electrons settled into orbit around the cores. They formed the first complete, whole, neutral atoms. Hydrogen atoms, helium atoms, a few lithium atoms. For the first time, the universe was filled with intact, stable atoms, with no loose electrons wandering around to scatter the light. And because the loose electrons were gone, the light could suddenly travel freely. The photons, which had been bouncing around in the fog for hundreds of thousands of years, were released. They streamed out in all directions, moving in straight lines at last. The universe became transparent. The fog lifted. And those first photons, the light that was released at the moment the atoms formed, have been traveling through space ever since. They are still traveling today. We can still detect them. They form a faint, even glow that fills the entire sky, coming from every direction. This glow is called the cosmic microwave background. The name sounds technical, but the idea is simple. It is the leftover heat from the early universe, cooled by the expansion of space over billions of years, now appearing as a very faint microwave signal. It is the echo of the moment when the first atoms formed, the fossil light of the universe's first great transition. We will talk more about it soon, but for now, just know this. The first atoms had formed. The universe was no longer a plasma. It was a gas, a vast, dark, expanding ocean of hydrogen and helium gas, with the light of that first release streaming out into the new darkness. The stage was set for the next long chapter. The quiet chapter, the dark chapter, the time before the stars, and we will drift into that dark together soon. We are drifting now into the quiet chapter, the long dark, the time after the first atoms formed and before the first stars began to shine. This stretch of the story has a name. It is sometimes called the Cosmic Dark Ages. The name sounds somber, and in a way it is, but it is also peaceful. It is a time of stillness, a time of waiting, a time when the universe was vast and dark and almost perfectly silent, and yet, within that silence, something patient and steady was already at work. Let us take a moment to picture the universe as it was at the start of this long dark. The fog had just lifted. The first atoms had formed. The light that had been trapped in the plasma for hundreds of thousands of years had been set free. That light, the cosmic microwave background, was streaming out in all directions, filling the universe with a faint, even glow. But that glow was not the light of stars. It was the leftover heat of the Big Bang itself, stretched and cooled by the expansion of space. And as the universe continued to expand, that light stretched further. Its wavelength grew longer. Its energy dropped. It shifted from visible light into infrared and then into microwaves, becoming fainter and cooler all the time. Today, billions of years later, we can still detect it. It is the oldest light in the universe, the faint whisper of the moment when atoms were born. But in the time we are describing now, it was still relatively fresh, still relatively warm, and then, as the expansion continued, it faded. It cooled, and the universe grew dark. Not dark in the way a room is dark when you turn off the light, dark in a deeper sense. Dark because there were no sources of new light anywhere, no stars, no galaxies, but no glowing embers, just a vast, expanding ocean of hydrogen and helium gas, with a few traces of lithium. The gas was spread out, almost perfectly smooth, with only the tiniest ripples of density here and there. These ripples were not much, just slight variations in how much gas was in one place versus another. Some regions were a tiny bit denser than average, some were a tiny bit less dense. These variations were the seeds of everything that would come later. They were the faint blueprint of the universe, imprinted in the very first moments, stretched by inflation, and now lying dormant in the dark. And within this dark, something was beginning to work, something slow and patient and utterly relentless. Gravity. Gravity is the great sculptor of the universe. It is the force that pulls mass toward mass. Every atom in the universe exerts a gravitational pull on every other atom. The pull is tiny, almost too tiny to notice on the scale of individual particles, but it never stops, it never rests. It is always there, always working, always pulling, and over enough time, even the tiniest pull can shape the largest structures. In the Dark Ages, gravity had time, plenty of time. Hundreds of millions of years of quiet, uninterrupted time, and so it began its work. In those regions where the gas was just slightly denser than the surrounding space, gravity had a little more to work with. The denser regions pulled on the gas around them, drawing more gas in. As more gas fell in, those regions became even denser, which made their gravitational pull even stronger, which drew in still more gas. This is a slow, patient feedback loop, a self-reinforcing process. The rich get richer, in a gravitational sense. The slightly dense regions become denser. The voids between them become emptier. And so, over millions of years, the smooth, almost featureless gas of the early universe began to develop structure. It began to clump. It began to gather into vast, diffuse clouds, then into denser filaments, then into knots and sheets and webs of gas stretching across the dark. This process was incredibly slow by human standards. We are talking about timescales of tens of millions of years, hundreds of millions of years. There was no rush, there was no deadline. The universe had all the time it needed, and gravity was patient. It pulled gently, steadily, without hurry. The gas clouds grew and contracted, slowly collapsing under their own weight. As they collapsed, they heated up. The same principle applied here that applied in the Big Bang. When gas is compressed, it heats. The atoms in the collapsing cloud moved faster and faster as they fell inward. The cloud grew denser and hotter at its center, and gravity kept pulling. This is the deep, quiet rhythm of the Dark Ages. Gas, gravity, and time. Three ingredients, working together in the dark. No light, no fire, no spectacle, just the slow, silent gathering of matter. The universe was a vast, dark ocean, and within that ocean, currents were forming. Gravity was pulling the gas into streams and pools and eddies. The cosmic web was beginning to take shape, a sponge-like structure of filaments and voids, with dense knots at the intersections of the filaments. These knots would one day become the cradles of galaxies. But for now, they were just dense clumps of dark, invisible gas, slowly contracting, slowly heating, waiting. It is worth pausing here to sit with the sheer length of this dark time. The cosmic Dark Ages lasted for something like a few 100 million years. Let that number settle. A few 100 million years. The entire history of life on Earth, from the first single-celled organisms to this moment right now, fits several times over into just this one quiet chapter. Dinosaurs rose and fell in a fraction of this time. Human civilization is a blink compared to this stretch. And through all of it, there was nothing but dark gas, slowly moving, slowly gathering. No eyes to see it, no ears to hear it, no mind to wonder at it. Just the quiet working of gravity, pulling atom toward atom, building the foundations of everything that was to come. If you had been able to float in that early universe, suspended somehow in the dark, you would have seen nothing. Not the darkness of a cloudy night, where the stars are hidden but you know they are there. A deeper darkness, an absolute darkness. A darkness with no stars, no planets, no moons, no sources of light at all except for the fading glow of the cosmic microwave background, which by then had cooled so much it was no longer visible to human eyes. You would be surrounded by hydrogen and helium gas, but you would not see it. It would be too thin, too diffuse, too dark. You would feel no wind, hear no sound. Just a vast, silent, empty-seeming dark. And yet, within that dark, gravity was working. The seeds of galaxies were growing. The universe was preparing itself for the next great transition, the dawn. And that dawn was coming. As the gas clouds collapsed further, as the dense knots at the centers of the filaments grew hotter and denser, they were approaching a critical threshold, a temperature and density at which something new would become possible. The cores of these collapsing clouds were getting hotter and hotter. When a gas is compressed enough, its atoms collide with such force that they can fuse together. Two hydrogen nuclei can be forced to merge, releasing energy in the process. This is nuclear fusion. This is the process that powers stars. And in the deepest, densest hearts of these collapsing gas clouds, the conditions for fusion were almost ready. Almost, but not quite. The Dark Ages were not over yet, but they were drawing to a close. Let us linger here, in the dark, just a little longer. There is no rush to leave. The Dark Ages are a good place to rest. They are the quietest part of our story, the most peaceful part. The heat of the Big Bang is behind us. The complexity of stars and galaxies and life is ahead of us. But here, in the long dark, there is nothing but gravity and gas and time. A slow, silent waltz of invisible forces, a patient preparation. The universe is gathering its breath before the next great leap. And we can gather our breath too. We can let the stillness of the Dark Ages settle over us like a blanket. The slow pull of gravity, the quiet contraction of gas, the patient accumulation of matter. These are sleepy processes. They happen on timescales that make a human life feel like a single exhale. And that is a comforting thought, not a frightening one. The universe is not in a hurry. Gravity is not in a hurry. And you, lying here in the dark, do not need to be in a hurry either. You can drift. You can float in the quiet, like one of those ancient hydrogen atoms, pulled gently by forces too slow to feel. The dark is soft. The dark is long. The dark is full of quiet work, invisible and patient. And soon, very soon, the first light will bloom. But not yet. Not quite yet. We are still in the Dark Ages, still in the quiet, still drifting, and that is exactly where we are meant to be. The Dark Ages are coming to an end. The long, quiet stretch of waiting is almost over. For hundreds of millions of years, gravity has been working in the dark, pulling the gas together, gathering it into denser and denser clumps. And now, in the deepest hearts of those clumps, something new is about to happen. The universe is about to light up for the first time since the fading of the cosmic microwave background. The first stars are about to be born. Let us return to those dense knots of gas we left drifting in the dark. Over the millions of years that passed, gravity kept pulling. The gas kept collapsing. The cores of these collapsing clouds grew hotter and denser, bit by bit, degree by degree. Remember the rule we have been following throughout this story. When gas is compressed, it heats up. The atoms fall inward, picking up speed, colliding with each other more and more violently. The temperature at the center of a collapsing gas cloud rises and rises, and as the temperature rises, the atoms move faster, they collide harder, and if the temperature rises high enough, something fundamental changes. The collisions become so violent that the atoms cannot bounce off each other cleanly anymore. Instead, they smash together and stick. They fuse. Two hydrogen nuclei, two single protons, are forced together by the sheer violence of their collision. They overcome the electric repulsion that normally keeps them apart. And when they fuse, they form a helium nucleus, and they release a burst of energy. This is nuclear fusion. This is the process that makes a star a star. This is the moment when a dark clump of gas becomes a shining, self-sustaining ball of light. The first stars ignited in the densest cores of the collapsing clouds. They were the first new light the universe had seen since the Big Bang itself. This moment, this turning point, is sometimes called cosmic dawn. It is a fitting name. For the first time in hundreds of millions of years, the universe had light, real light, starlight. Photons were being created not from the leftover heat of the Big Bang, but from the fusion fires in the hearts of these new stars. The Dark Ages were over, the age of stars had begun. But these first stars were not like the stars we see in the night sky today. They were different. They were born from gas that was almost perfectly pure hydrogen and helium. There was no carbon, no oxygen, no iron, no heavier elements of any kind in the mix. Those elements had not yet been made. They would only be created later, inside stars, and scattered into space when those stars died. But the first stars formed before any of that had happened. They were made of the simplest, lightest ingredients, and that made them behave differently than the stars we are used to. We believe that the first stars were enormous, much larger than our Sun. Some of them may have been hundreds of times more massive. The reason for this has to do with how stars form. When a cloud of gas collapses, it tends to heat up, and that heat pushes back against further collapse. It creates a kind of pressure that slows the inflow of more gas. In the modern universe, heavier elements like carbon and oxygen help the gas cool down more efficiently, allowing it to collapse into smaller clumps and form smaller stars. But in the early universe, those heavier elements were not available. The gas could not cool as easily, so the collapsing clouds stayed hotter and the heat pushed back, and the result was that only the very largest clumps could overcome the heat and collapse all the way to ignition. The first stars, therefore, tended to be giants, massive, hot, and blazingly bright. It is important to say, calmly and plainly, that we have never directly seen one of these first stars. They are too far away, too far back in time, for our telescopes to pick them out individually. Our understanding of them comes from theory, from computer models, from the known laws of physics applied to the conditions of the early universe. The exact details of how they formed, how large they were, how long they lived, are still debated among the people who study them. There is genuine uncertainty here. The not knowing is part of the story, just as it has been at other points along the way. We have a broad outline that is well supported, but the fine details are still being worked out, and that is all right. We can hold the broad outline gently and let the details remain soft at the edges. What we can say with confidence is that these first stars were short-lived by cosmic standards. The largest stars burn through their fuel very quickly. A star 100 times the mass of our Sun might live for only a few million years, compared to the 10 billion-year lifetime of a star like our Sun. The more mass a star has, the hotter and faster it burns. It is a little like a candle that burns at both ends. The light is brilliant, but the flame does not last. The first stars blazed brightly and briefly against the dark, and then they died, and their deaths were spectacular. They went out in enormous explosions, scattering their newly forged heavy elements into space. But we are getting ahead of ourselves. That is a story for a later section. For now, we are still at the moment of ignition, the moment when the first light bloomed in the dark. Picture it, if you can. Not as a single event, but as a gradual process. The first stars did not all turn on at once, like a bank of lights being switched on. They ignited one by one, in different places, at different times, as different gas clouds reached the critical threshold. The dark universe began to be dotted with points of light, small, isolated pockets of brilliance in the vast, dark ocean. Each one was a star. Each one was a fusion furnace, turning hydrogen into helium, pouring light and heat into the surrounding space. And as more and more of them ignited, the universe began to change. The Dark Ages gave way to a new era, an era of light, an era of stars. The light from those first stars began to travel outward, pushing back the darkness. It began to heat the surrounding gas. It began to ionize the hydrogen atoms that filled the space between the stars, stripping the electrons away from the protons once again. This process, the re-ionization of the universe, was the next great transition after the formation of atoms. The universe had been neutral, filled with whole atoms, for hundreds of millions of years. Now, the fierce light of the first stars was breaking those atoms apart again, turning the space between stars back into a plasma. Not everywhere, not all at once, but gradually, patch by patch, the universe was being transformed by starlight. This period, the era of the first stars and the re-ionization they caused, is a bridge between the Dark Ages and the universe we recognize today. It is the time when the cosmos began to take on structure and complexity. The first stars were not just sources of light, they were also the first factories for heavy elements. In their hot, dense cores, they began the process of building carbon, oxygen, nitrogen, and other elements from the raw hydrogen and helium. And when they died, they scattered those elements into space, enriching the gas clouds around them. The next generation of stars would be born from gas that was no longer perfectly pure. It would contain a small amount of heavier elements, and that small amount would make a big difference. It would allow smaller stars to form, stars like our Sun, stars that could live long, stable lives with planetary systems around them. The first stars were the pioneers. They were the ones that prepared the way for everything that followed. They broke the darkness. They seeded the cosmos with the raw materials for planets and for life, and then they died, passing the torch to the generations that came after. But we are still in the moment of their birth, the first light, the cosmic dawn. Let yourself drift into that image. A dark universe, slowly being dotted with points of light, like the first stars coming out at twilight, but stretched across the whole sky, across all of space. One by one they flicker on, each one a small, fierce beacon in the dark, each one a sign that the quiet chapter is ending and a new chapter is beginning. The universe is waking up. The long sleep of the dark ages is giving way to the bright, busy, complex age of stars and galaxies. And we are here to watch it happen, slowly, from the quiet of our own dark room, our own small point in space and time. The first stars are burning. The cosmic dawn has arrived. And the story is moving forward, into the light. The first stars are burning now. They are scattered across the universe, each one a point of light in the vast dark. But stars, as bright and as important as they are, do not stay alone for long. Gravity is still working. It never stopped working. And now it has more to work with. It has stars, it has gas, it has the heavier elements that the first stars have begun to make. All of these things are pulling on each other, and over millions of years, they are being drawn together into larger and larger structures. The single stars are gathering into groups. The groups are gathering into larger groups. The universe is beginning to take on a new shape, a shape we recognize, the shape of galaxies. A galaxy is a vast collection of stars, gas, and dust, all held together by gravity. Our own sun is part of a galaxy. We call it the Milky Way. On a dark night, far from city lights, you can see it as a faint, cloudy band stretched across the sky. That band is the combined light of hundreds of billions of stars, so far away that they blur together into a soft, milky glow. Every one of those stars is a sun, and many of them have planets of their own. The galaxy is our home in the universe. It is the largest structure we can see with our own eyes. And it began to form, like all galaxies, in the era we are describing now. How did galaxies form? The process was slow and patient, like everything else in this story. It began with those slight ripples in density that were imprinted in the universe during the very first moments. During the Dark Ages, gravity had been pulling gas toward the denser regions. Those regions became the filaments and knots of the cosmic web. When the first stars ignited, they were born inside these dense knots. They were clustered together from the start, because the gas that formed them was already clustered. As more and more stars formed in the same general region, their collective gravity began to bind them together. They started to orbit around a common center. A small, early galaxy was taking shape. But there was more going on than just the visible matter. There was something else at work, something we cannot see directly, something whose true nature remains one of the great open questions of our story. We have to talk about it now, because without it, galaxies as we know them would not exist. The name we give to this unseen thing is dark matter. The name is a placeholder, an honest admission of not knowing. Dark matter is a form of matter that does not interact with light. It does not shine. It does not reflect. It does not absorb. It is invisible. We know it is there because of its gravity. It pulls on the things we can see. In fact, it seems to make up most of the matter in the universe. There is far more dark matter than there is ordinary matter, the kind of matter that makes up stars and planets and you and me. The ordinary matter is like the thin frosting on a cake. The dark matter is the dense, invisible body of the cake itself. What dark matter actually is, we do not know. We have ideas. We have possibilities. We have experiments running right now, deep underground, trying to catch a dark matter particle passing through. But so far, none of them have succeeded. The nature of dark matter is genuinely unknown. It is one of the central mysteries of modern cosmology. And that is all right. We can name the mystery without needing to solve it. We can say that dark matter is there, and that it was essential, and that we do not know what it is. The not knowing is woven into the story, as it has been from the very beginning. Why was dark matter so important for galaxies? Because it provided the gravitational scaffolding. The dark matter, which had also been pulled into the dense regions of the cosmic web, formed vast clumps and halos. These dark matter halos were much larger and more massive than the clumps of ordinary gas. Their gravity was immense. The ordinary gas, the hydrogen and helium that would form stars, was pulled into these dark matter halos. The halos acted like gravitational wells, deep pits in the fabric of space that collected the visible matter. At the bottom of these wells, the gas gathered and cooled and formed stars. The stars then clumped together into galaxies. So every galaxy we see, including our own, is thought to sit inside a much larger invisible halo of dark matter. The dark matter is the hidden frame. The visible galaxy is the bright picture stretched across it. This process took hundreds of millions of years. The first small galaxies, sometimes called proto-galaxies, were not as large or as organized as the galaxies we see today. They were smaller, messier, more irregular in shape. But they had gravity, and gravity kept pulling. It pulled on the gas within them, forming more stars, and it pulled on neighboring proto-galaxies, drawing them together. Galaxies grew by merging. When two galaxies came close enough, their mutual gravity would pull them into a slow, spiraling dance. Over millions of years, they would swing around each other, pass through each other, and eventually settle into a single, larger galaxy. This is how galaxies got bigger over time, not just by forming new stars from gas, but by combining with other galaxies. The universe was a place of slow, quiet collisions. Great swirls of stars passing through each other, their shapes distorted by gravity, their gas clouds compressed into bursts of new star formation, until at last they merged into a new, larger whole. This merging process is still going on today. Our own Milky Way is on a slow collision course with a neighboring galaxy called Andromeda. In about 4 or 5 billion years, the two galaxies will begin to merge. They will swing through each other, their stars mingling, their shapes stretching and warping, until they eventually settle into a single, enormous elliptical galaxy. But that is far in the future. In the era we are describing now, the merging was far more common. The universe was smaller, denser, and galaxies were closer together. Collisions and mergers were frequent. The large, majestic spiral galaxies we see today, like the Milky Way, were built up from countless smaller galaxies that merged over billions of years. The Milky Way itself began forming during this general era. The exact details of its early history are still being studied, but we know that it grew, like all galaxies, by gathering gas and merging with smaller neighbors. Some of the stars in the Milky Way today are very old, almost as old as the universe itself. They formed in the first few 100 million years and are still shining, still orbiting the galactic center, faint and cool and red with age. These ancient stars are like fossils, carrying the history of the galaxy's early days in their chemical makeup. They tell us that the Milky Way has been building itself, slowly and patiently, for most of the universe's life. As galaxies grew and matured, they began to develop structure. The gas and stars settled into disks, often with spiral arms winding outward from the center. At the very center of most large galaxies, including our own, a supermassive black hole formed. These black holes are incredibly dense objects whose gravity is so strong that not even light can escape them. They can be millions or even billions of times the mass of our Sun. How exactly they formed so early and grew so large is still a matter of active research and genuine uncertainty. But they are there, sitting at the hearts of galaxies, their immense gravity influencing the motion of stars around them. All of this structure, the spiral arms, the central bulges of stars, the dark matter halos, the supermassive black holes, emerged from the same slow, patient process. Gravity, gas, time. The universe was now a place of vast, organized structures. Galaxies were grouped into clusters, and clusters into superclusters. The cosmic web, the sponge-like pattern of filaments and voids, was now illuminated by the light of stars and galaxies. The Dark Ages were a distant memory. The universe was bright and complex and busy, and the story was about to move inward, from the scale of galaxies to the scale of individual stars, to the lives of stars and their deaths. Because it is in the lives and deaths of stars that the heavier elements were made. The carbon, the oxygen, the iron. The elements that would one day form planets and oceans and living bodies. The story of galaxies is the story of structure, but the story of stars is the story of chemistry. And we are about to drift into that story now, slowly, into the heart of a star, where light and matter dance together in the deep, slow furnace of creation. Let us move inward now, away from the vast scale of galaxies and clusters, away from the cosmic web stretching across billions of light years. Let us move closer, much closer, to the scale of a single star, a single point of light in the dark. And let us spend some time with that star. Let us watch it live its life. Because stars are not static. They are not eternal. They are born, they live, they grow old, and they die. And their lives and deaths are the reason we are here. The heavier elements that make up our world, our bodies, our air, our oceans, all of them were made inside stars. The carbon in every cell, the oxygen in every breath, the iron in our blood, the calcium in our bones, all of it was forged in the heart of a star, long ago, and scattered into space when that star died. We are, in a very literal sense, made of stardust. And the story of how that happened is the story we are about to tell. A star shines because of what is happening in its core. The core of a star is a place of extreme heat and extreme pressure. The weight of all the layers of gas above the core presses down with tremendous force. That pressure, combined with the heat, is enough to force atomic nuclei together. This is the same process of fusion we spoke of when the first stars ignited. Two hydrogen nuclei, two single protons, are pushed together so hard that they overcome their natural repulsion and merge. When they merge, they form a helium nucleus, and they release a small amount of energy. That energy, multiplied by the trillions upon trillions of fusion reactions happening every second, is what makes the star shine. It is what pushes back against the crushing weight of gravity. A star is a balance, a delicate equilibrium. Gravity is trying to crush the star inward. The energy from fusion is trying to blow it outward. For most of a star's life, these two forces are in perfect balance. The star is stable. It shines steadily, for millions or billions of years, depending on its size. This process of fusing hydrogen into helium is the main business of a star's life. It is what our own sun is doing right now, and has been doing for about 4.5 billion years. It is a slow, steady, patient process. The sun converts about 600 million tons of hydrogen into helium every single second. That sounds like a lot, and it is. But the sun is so vast that it can keep this up for another 5 billion years or so before it runs out of hydrogen fuel in its core. The sun is middle-aged. It is in the long, stable middle of its life, burning hydrogen steadily, shining with a calm, reliable light. That calm, reliable light is the reason life on Earth is possible. It is the reason you are here, lying in the dark, listening to these words. A steady star, a stable balance, a long, patient middle age. But not all stars are like our sun. Some are much larger. Some are smaller, and the size of a star determines everything about its life. The smallest stars, the red dwarfs, are only a fraction of the sun's mass. They burn their fuel so slowly and so efficiently that they can live for trillions of years, far longer than the current age of the universe. No red dwarf has ever died of old age. They are all still in their infancy, relatively speaking, slowly and quietly burning hydrogen. At the other end of the scale are the massive stars. Stars that are 10, 20, 50 times the mass of our sun. These stars live fast and die young. Their greater mass means greater gravity, which means greater pressure and heat in the core, which means they burn their fuel at a furious rate. A star many times the mass of the sun might live only a few million years, compared to the sun's 10 billion year lifetime. The brightest flames burn out the soonest. And it is in these massive stars that the real work of building heavier elements takes place. A star like our sun will spend its life fusing hydrogen into helium, and near the end of its life it will fuse some helium into carbon and oxygen. But it will go no further. It does not have enough mass to create the pressures and temperatures needed to fuse heavier elements. The truly massive stars, however, do. In their cores, after the hydrogen is exhausted, they begin fusing helium into carbon, then carbon into oxygen, then oxygen into neon, neon into magnesium, magnesium into silicon, and silicon into iron. The core of a massive star becomes a kind of cosmic onion, with layers upon layers of different elements. Hydrogen fusing to helium on the outside, helium fusing to carbon one layer in, and deeper through layer after layer, each one fusing a heavier element from the ash of the layer above it, until finally, at the very center, there is a core of iron. Iron is a special element. It is the end of the line for fusion. All the fusion reactions up to iron release energy. That energy is what powers the star and holds off the crush of gravity. But iron is different. To fuse iron into something heavier, you have to put energy in. It does not release energy. So when a massive star builds up a core of iron, the fusion engine at its center simply shuts down. There is no more energy being produced to push back against gravity. And gravity, which has been waiting patiently for millions of years, finally wins. What happens next is swift and violent. The iron core collapses under its own weight. In less than a second, a core that was thousands of miles across is crushed down to a sphere only a few miles wide. The collapse releases an enormous amount of gravitational energy. The outer layers of the star come crashing down onto this ultra-dense core and then rebound outward in a titanic explosion. This explosion is called a supernova. For a brief time, a single star can outshine an entire galaxy. Its light can be seen across billions of light years. And in that explosion, in that furious burst of energy and neutrons and heat, the heaviest elements are forged, everything heavier than iron. The gold, the silver, the platinum, the uranium, all of it is made in the furnace of a supernova, in the dying moments of a massive star. And then those elements are scattered into space, flung outward in vast, expanding clouds of gas and dust. The star has died, but in dying, it has seeded the universe with the raw materials for planets, for oceans, for life. This process, this cycle of birth and death and rebirth, has repeated across the history of the universe, generation after generation of stars, each generation born from the ashes of the ones that came before, each generation enriching the gas clouds a little more. The early universe had only hydrogen and helium, and a trace of lithium. But today, billions of years later, the gas in our galaxy is enriched with carbon, oxygen, nitrogen, iron, and all the rest. Every new star that forms today, including stars like our sun, forms from gas that has been through this cycle many times. The sun is not a first-generation star. It is a later generation star, made of recycled material, and the planets around it, including Earth, are made of that same recycled material. The iron in Earth's core, the silicon in its rocks, the oxygen in its oceans. All of it was made in stars that lived and died long before our sun was born. Let that thought settle. The atoms that make up your body have been through this cycle. The carbon in your cells was made in the core of a star. The oxygen you breathe was made in the core of a star. The iron in your blood was forged in a supernova. These atoms have existed for billions of years, cycling through stars, through gas clouds, through planets, through living things. They are ancient travelers, and for a brief moment, they have come together to form you. That is not a metaphor. It is a plain, scientific fact. The elements heavier than hydrogen and helium are stardust, and we are made of them. The story of stars living and dying is also the story of how the universe became a place capable of supporting life. Without the heavier elements, there would be no rocky planets, no water, no air, no complex chemistry. The first stars lit up the dark, but the generations that followed made the universe habitable. They built the periodic table, element by element, and scattered it across space. They prepared the ground for us, and they did it over timescales so vast that our minds can barely hold them. Billions of years, generations of stars, a slow, patient cosmic ecology of birth and death and renewal. Now, as we near the end of this section, let us pull back for a moment and look at the whole picture. The universe is full of galaxies, each one full of stars. In those stars, fusion is happening, turning hydrogen into helium and building the heavier elements. Some of those stars will die in supernovae, scattering their elements into space. Those elements will mix with gas, form new clouds, and collapse into new stars and new planets. The cycle continues. It has continued for most of the universe's history, and it will continue for a long time yet. But we are going to leave that vast, repeating cycle now and narrow our focus again. We are going to look at one particular cloud of gas and dust, enriched by earlier generations of stars. One particular patch of the Milky Way galaxy, because about 4,600,000,000 years ago, something happened in that patch. A cloud began to collapse. A new star began to form. Our star, our sun. And the story of that sun and the planets that formed around it is the next chapter. The chapter that leads, step by slow step, to you. We are narrowing our focus now. We are leaving behind the vast, repeating cycle of stars being born and dying across the whole universe. We are turning our attention to one particular patch of space. One particular cloud of gas and dust floating in the Milky Way galaxy about 4,600,000,000 years ago. This cloud was not special. It was one of countless similar clouds scattered throughout the galaxy at that time. It was made mostly of hydrogen and helium, like all gas clouds. But it was also enriched with heavier elements: carbon, oxygen, nitrogen, iron, elements that had been forged in the cores of earlier stars and scattered into space by supernovae. This cloud was the raw material for something new, and it was about to begin the slow, patient process of collapse. What caused the collapse? We do not know for certain. It could have been the shock wave from a nearby supernova, compressing the gas as it passed through. It could have been the gravitational pull of a passing star, or a spiral arm of the galaxy sweeping through and gently squeezing the cloud. Or it could simply have been that enough gas had gathered in one place over millions of years that its own gravity finally overcame the internal pressure that had been holding it up. Whatever the trigger, the result was the same. The cloud began to contract. Gravity began to pull the gas inward, toward the center of the cloud. And once that process started, it fed on itself. The more the cloud contracted, the stronger its gravity became. The stronger the gravity, the faster the contraction. A slow, inevitable collapse had begun. As the cloud collapsed, it did not fall straight inward all at once. The cloud was not perfectly still. It had some small amount of spin, some slight rotation, probably from the random motions of the gas within it. As the cloud contracted, that spin increased. This is a basic principle of physics. When a spinning object pulls its mass inward, it spins faster. Think of an ice skater pulling in their arms during a spin. The cloud did the same thing. As it collapsed, it spun faster and faster. And because it was spinning, the gas did not all fall straight to the center. The spin flattened the cloud into a disk. A vast, rotating disk of gas and dust, with the densest part at the very center. At the center of this disk, the gas was thickest and hottest. The pressure and temperature were rising steadily as more and more gas fell inward. This central clump was becoming a protostar. A protostar is a star that is not yet a star. It is a dense, hot ball of gas that is still gathering mass from the surrounding disk. It glows, but not from fusion. It glows from the heat of its own contraction, from the gravitational energy released as gas falls onto it. It is a star in the process of being born. And it would take millions of years for the protostar to gather enough mass and reach enough heat and pressure in its core for nuclear fusion to ignite. But when that moment came, it would be the birth of our sun. While the protostar was growing at the center, the disk of gas and dust around it was also busy. The disk was not uniform. It had clumps and ripples and variations in density, just as the early universe had. In the denser parts of the disk, the same process that formed the protostar began to repeat on a smaller scale. Gravity pulled dust grains and gas molecules together. They stuck. They formed larger clumps. Pebbles became boulders. Boulders became larger rocks. These rocks collided and merged, growing into bodies called planetesimals, which were essentially small, irregular chunks of rock and ice, maybe a few miles across. Over millions of years, these planetesimals continued to collide and stick together, growing larger and larger. This process is called accretion. It is a slow, messy, violent process of building planets from countless smaller pieces. But given enough time, it works. In the inner part of the disk, close to the protostar, it was too hot for ice to exist. Only rocky material and metals could condense out of the gas. So the planets that formed in the inner disk were rocky, small, dense, made of silicates and iron. In the outer part of the disk, it was cold enough for ice to exist. Water ice, methane ice, ammonia ice. So the planets that formed in the outer disk were larger, and they gathered thick envelopes of gas around their icy cores. These became the gas giant planets: Jupiter, Saturn, Uranus, Neptune. The solar system was taking shape, with small rocky worlds near the center and large gaseous worlds farther out. One of those rocky worlds was Earth. But Earth did not form in isolation. The early solar system was a chaotic place. There were dozens, perhaps hundreds of protoplanets, all competing for material, all on unstable orbits. Collisions were frequent. Some protoplanets were destroyed, some were absorbed into larger bodies. One of these collisions, we believe, was between the young Earth and a Mars-sized object. The impact was not a direct head-on crash, but a glancing blow. It shattered the other object and blasted a huge amount of material from Earth's outer layers into orbit. That orbiting debris eventually coalesced under its own gravity to form our moon. This is the leading explanation for how the moon was made. It is called the giant impact hypothesis. It is well supported by evidence, but it is worth noting that the exact details are still being studied and debated. The early history of our solar system is something we are still piecing together, bit by bit, from the clues left behind in rocks and craters and the orbits of the planets. After about 10 million years, the protostar at the center of the disk reached the critical temperature and pressure in its core. The temperature hit about 10 million degrees. At that temperature, hydrogen nuclei began to fuse into helium. Fusion ignited. The star turned on. Our sun was born. The sudden burst of energy and radiation from the newborn sun swept through the inner solar system. The solar wind, A stream of charged particles flowing outward from the sun cleared away much of the remaining gas and dust from the disk. The planets were left in their orbits, circling the new star. The era of planet formation was largely over. The sun, now a stable, shining star, settled into its long middle age. The planets settled into their orbits. The solar system became the organized, clockwork system we know today. Mercury, Venus, Earth, and Mars, orbiting close to the sun. The asteroid belt, a leftover band of rocky debris, orbiting between Mars and Jupiter. Jupiter, Saturn, Uranus, and Neptune, orbiting farther out. And beyond Neptune, the Kuiper belt, a vast disk of icy bodies, remnants from the outer solar system's formation. The raw material for all of this had come from earlier generations of stars. The iron in Earth's core, the silicon in its rocks, the carbon, the oxygen, the nitrogen, all of it had been forged in stellar furnaces and supernova explosions, long before the sun was even a twinkle in the cosmic eye. The cloud that collapsed to form our solar system was a cloud of recycled stardust, and that stardust became our home. It became the ground beneath your feet. It became the air you breathe. It became the raw ingredients for life itself. And that is where the story is going next, to Earth. To the cooling of the young planet, to the formation of oceans, to the slow, mysterious emergence of the first living things. The stage is set, the sun is shining, the planets are in their orbits, and on one of those planets, a small, rocky world, something extraordinary is about to happen. Or perhaps not extraordinary. Perhaps, given the right conditions and enough time, it is simply what the universe does. We do not know, and that not knowing is part of the calm. We will carry it with us, gently, as we drift down to the surface of the young Earth. In the next part of our story, the sun is born. The planets are formed, the journey continues, and there is still so much time ahead. So much time. We are drifting down now, down through the thin veil of the early solar system, down toward the third planet from the newly ignited sun, Earth. It is young, only a few tens of millions of years old, and it is nothing like the blue and green world we know today. It is a place of fire and rock and relentless, pounding violence. The final stages of planetary formation are still underway. The young Earth is being bombarded by leftover planetesimals, chunks of rock and ice that were never incorporated into the planets. Each impact delivers a blast of heat, melting the surface, blasting out craters, adding a little more mass to the growing world. The Earth is, at this stage, largely molten, a vast, glowing sphere of liquid rock, with no solid ground, no oceans, no air that we could breathe. The heat comes from two sources. The first is the leftover heat of formation, the gravitational energy of all those countless collisions turned into thermal energy. The second is radioactivity. Deep inside the Earth, heavy elements like uranium and thorium, forged in supernovae long before the sun was born, are decaying. Their atomic cores are breaking apart, and in doing so they release heat. That heat is still there today, still keeping the Earth's deep interior warm, still driving the slow churn of the mantle and the drift of continents. But in the young Earth, it was far more intense. Slowly, over tens of millions of years, the bombardment began to ease. The solar system was clearing itself of the leftover debris. The largest chunks had already been swept up by the planets. The rate of impacts declined, and as the impacts declined, the Earth began to cool. The surface, which had been a global ocean of molten rock, began to solidify. A thin, fragile crust of solid rock formed, floating on top of the still molten mantle below. It was dark and brittle and constantly cracking, constantly being reshaped by the heat and motion beneath it. Volcanoes poured out lava and gases from the interior. There was no life yet, no plants, no animals, no microbes even, just rock and fire and the thin, tentative crust forming and breaking and forming again. But one of the most important things was happening invisibly. The volcanoes were releasing gases, water vapor, carbon dioxide, nitrogen, methane, ammonia. These gases, trapped inside the Earth's interior since its formation, were being belched out into the space around the planet. Over millions of years, they built up a blanket around the Earth, a first atmosphere. It was not the atmosphere we breathe today. There was no oxygen. It was a thick, heavy, toxic mix of gases. But it was an atmosphere. It held heat close to the surface. It shielded the young Earth from the worst of the sun's radiation. And it contained water vapor, a great deal of water vapor. As the Earth continued to cool, something pivotal happened. The temperature dropped enough for that water vapor to condense. It began to fall as rain. Torrential, endless rain. For millions of years, rain fell from the thick, hot clouds onto the bare, volcanic rock of the young Earth. The rain fell and fell and fell. It flowed into the low places on the crust, pooling in the great basins and depressions. It carried dissolved minerals from the rocks. It collected and deepened. The first oceans were forming, not all at once, but gradually, over an immense stretch of time. The Earth was becoming a water world, a planet with liquid water on its surface. That liquid water would turn out to be the key ingredient. As far as we know, life requires liquid water. It needs a solvent, a medium in which the complex chemistry of life can unfold. And the young Earth now had that. It had vast, warm, shallow oceans, rich with dissolved minerals, under a thick atmosphere, bathed in the steady light of the young sun. And then, something happened that we still do not fully understand. Life appeared. We know, from the evidence in ancient rocks, that life was present on Earth very early. The oldest confirmed fossils of living organisms are about 3.5 billion years old. But there are chemical traces, subtle signatures in the carbon in ancient rocks, that suggest life may have been present even earlier. Within about 1 billion years of Earth's formation, and possibly much sooner, the first living things were here. How did this happen? We do not know. This is one of the great open questions. It is genuinely unresolved. We have a broad understanding that life emerges from chemistry, that under the right conditions, simple molecules can combine into more complex molecules, that these complex molecules can become self-replicating, making copies of themselves, and that once self-replication begins, evolution by natural selection can take hold, driving the development of greater and greater complexity over time. But the exact steps from non-living chemistry to the first living cell are still a mystery. There are many ideas. None have been proven. The not knowing here is deep and real, and that is all right. We can sit with that mystery. We can let it be what it is. A quiet, open question at the heart of our own existence. What we do know is that once life appeared, it began to spread and diversify. The first living things were simple, single cells, tiny sacs of organic molecules capable of taking in nutrients, growing and dividing. They had no nucleus, no complex internal structures. They were, in the simplest terms, microscopic bags of life. They lived in the oceans, probably near sources of chemical energy. Some of them began to develop a remarkable ability, the ability to capture sunlight and use its energy to turn carbon dioxide and water into food. This is photosynthesis. The first photosynthesizers, called cyanobacteria, were a turning point in the history of life on Earth, because photosynthesis has a byproduct, oxygen. For the first time, oxygen gas was being produced and released into the environment. At first, the oxygen did not build up in the atmosphere. It reacted with the iron dissolved in the oceans, forming rust, which settled to the seafloor in great layers. It reacted with the rocks on the surface. It was absorbed by the environment, but after hundreds of millions of years, the environment became saturated. It could not absorb any more, and oxygen began to accumulate in the atmosphere. This is sometimes called the Great Oxygenation Event, though we do not need that label. The simple fact is that the atmosphere changed from one with almost no oxygen to one with a significant amount. This was a crisis for many of the early life forms for whom oxygen was toxic. It caused one of the greatest extinctions in Earth's history. but it also opened the door to new forms of life. Oxygen is a powerful source of energy. Organisms that could use it had a great advantage. They could grow larger. They could be more active. The stage was set for more complex life. And yet, for a very long time, life remained simple. For more than 2 billion years, the oceans were filled with single-celled organisms. Some of them formed mats and mounds called stromatolites, which still exist in a few places today, but nothing like a plant or an animal existed. The timescale here is almost beyond our ability to grasp. The Earth was already old by the time complex life appeared. More than half of the Earth's history had already passed. Life had been present for most of that time, but it was simple, patient, slow. The universe is not in a hurry, and life, it seems, is not in a hurry either. Then, around 600 million years ago, something began to change. The oxygen levels in the atmosphere had reached a point where larger, more complex bodies were possible. Cells began to cooperate, clustering together into multicellular organisms. At first simple, then more and more intricate. The first animals appeared, soft-bodied creatures, strange and unfamiliar to us, preserved as faint impressions in ancient rocks. Then, around 540 million years ago, came a great flourishing of animal life. This period, sometimes called the Cambrian explosion, saw the rapid appearance of most of the major animal body plans we see today: shells, exoskeletons, legs, eyes. The oceans became a bustling, complex ecosystem, and from those oceans, life began to move onto land. It is a long story, the story of life on Earth, and we will not trace every branch of it here. The point is simply the slow, patient unfolding. From single cells to complex cells, from complex cells to multicellular organisms, from the oceans to the land. Plants colonized the land first, followed by invertebrates, then vertebrates. Fish gave rise to amphibians. Amphibians gave rise to reptiles. Reptiles gave rise to dinosaurs, and also to mammals. The dinosaurs dominated the land for a very long time, about 165 million years. That is an immense span. And then, about 66 million years ago, a large asteroid struck the Earth, near what is now the Yucatan Peninsula. The impact triggered a mass extinction that wiped out the dinosaurs, along with many other forms of life. It was one of the worst days in Earth's history. But from the ashes, the mammals rose. They had been small, scurrying creatures, living in the shadow of the dinosaurs. Now, with the dinosaurs gone, they diversified, they spread, they grew larger, and among them, a particular branch, the primates, began to develop larger brains, complex social structures, hands that could grasp and manipulate objects, tools, language, consciousness. And eventually, after all of that, we arrived, human beings, able to look up at the night sky and wonder where it all came from, able to tell this story, in a quiet voice, in the dark, to someone who is drifting towards sleep. So here we are, the product of nearly 14 billion years of cosmic evolution, the iron in your blood, forged in a supernova, the water in your cells, delivered by ancient rain onto a molten earth, the oxygen you breathe, produced by countless generations of tiny bacteria, the complex structures of your body, built by billions of years of patient, incremental change. All of it has led to this moment, you lying here, warm, safe, listening. The story is almost done, but there are still a few chapters left. The chapter of where we stand now, in the vastness of the universe, and the chapter of what comes after. The long, slow future, the quiet end. But we will get to those soon. For now, just rest in the knowledge of this long, slow unfolding. From the first instant to the first cell, from the first cell to the first thought. The universe has come a long way, and you are here, at the end of it all, a witness to the story, a part of the story, drifting now into the quiet dark. So here we are, right now, this moment, you, lying in the dark, listening to a voice, Let us take a little time to understand where this moment sits in the grand scheme of things. Let us locate ourselves in the vastness we have been describing, because the story has brought us a long way, from the first instant, through the formation of atoms, through the long dark ages, through the birth of stars and galaxies, through the lives and deaths of countless suns, through the formation of our own solar system, through the emergence of life on this small, rocky world. All of that has led to now, to this quiet room, to this breath, to this heartbeat, and it is worth pausing to understand just where we are and what kind of universe we find ourselves in. Let us begin with our own home galaxy, the Milky Way. We spoke of it earlier, when galaxies were first taking shape, but now we can describe it from the inside, as the place where we live. The Milky Way is a spiral galaxy. It is shaped like a flat disk, with a central bulge of older stars and graceful spiral arms winding outward. If you could see it from above, it would look like a vast pinwheel of stars, gas, and dust, slowly turning in the dark. Our Sun is located in one of those spiral arms, about 2/3 of the way out from the center. The distance from the center of the Milky Way to our Sun is something like 27,000 light-years. A light-year is the distance light travels in 1 year, which is about 6 trillion miles, so 27,000 of those. It is a number too large to feel, and that is fine. We do not need to feel it. We just need to know that we are far from the center, in a quiet suburb of the galaxy, orbiting at a steady, unhurried pace. The Milky Way contains somewhere between 100 billion and 400 billion stars. That is a range, not a single number, because we cannot count them all precisely. But even the lower end of that range is staggering. 100 billion suns. Each one a star, like our own, or larger or smaller. Each one with its own story. Many of them, we now know, have planets. In the last few decades, we have begun to detect planets around other stars. We call them exoplanets, and we have found thousands of them. They are everywhere. Rocky worlds like Earth, gas giants like Jupiter, and strange kinds of planets we have no example of in our own solar system. The galaxy is full of worlds, and that is just our galaxy. The Milky Way is not alone. It is part of a small group of galaxies called the Local Group. The Local Group contains a few dozen galaxies, most of them small. The two largest are the Milky Way and a neighboring spiral galaxy called Andromeda. Andromeda is about 2.5 million light-years away. On a very dark night, in a very clear sky, you can see Andromeda as a faint, fuzzy patch of light. That light has traveled for 2.5 million years to reach your eyes. It left Andromeda before modern humans existed. That is how far away it is. And yet Andromeda is our closest large neighbor. In cosmic terms, it is right next door. Beyond the Local Group, the scale opens up even further. Galaxies are not scattered randomly. They are grouped into clusters, and clusters are grouped into superclusters. Our Local Group is part of a larger structure called the Virgo supercluster, which contains thousands of galaxies. And the Virgo supercluster is just one of many superclusters in the observable universe. The observable universe is the part of the universe we can see, the part from which light has had time to reach us since the beginning. It contains, we estimate, something like 200 billion galaxies, maybe more. 200 billion galaxies, each one with billions or even trillions of stars, each star a sun. Each sun with its own story, its own planets, its own possibilities. The numbers become so large that they stop feeling like numbers and start feeling like a kind of quiet, endless depth. And that depth is all around us. In every direction we look. The universe is vast beyond our ability to hold it in our minds. And we are here, in this one galaxy, on this one planet, in this one moment. A tiny, precious speck in an ocean of space and time. Now, let us remember something else about this universe. It is still expanding. The stretching that began in the first instant has never stopped. Space is still growing. The galaxies are still moving apart from each other, but there is something new to tell about this expansion. For most of the universe's history, the expansion was slowing down. This makes sense. Gravity pulls things together. All the matter in the universe exerts a gravitational pull on all the other matter. That pull should act as a brake on the expansion, slowing it down over time. And for the first several billion years, that is exactly what seems to have happened. The expansion was gradually slowing. But then, something changed. Around 5 or 6 billion years ago, the expansion stopped slowing down and began to speed up. The universe is not just expanding. The expansion is accelerating. Galaxies are moving away from each other faster and faster as time goes on. What is causing this acceleration? We do not know. The honest answer is that we do not know. We have given it a name. We call it dark energy. But the name is just a placeholder. It is an admission of not knowing. Dark energy is whatever is causing the expansion of the universe to speed up. It seems to be a property of space itself, a kind of energy that is spread evenly throughout the cosmos, pushing outward, counteracting gravity on the largest scales. It is not something we can see or touch or detect directly. We infer its existence from its effects. We see the distant galaxies moving away from us faster than they should be, if only gravity were at work. And we measure that acceleration, and we give it a name, and we say plainly that its true nature is unknown. It is one of the great mysteries of modern cosmology, like dark matter, like the question of what came before the beginning. The not knowing sits at the heart of our understanding, as it has from the very start of this story. What we do know is that dark energy seems to make up most of the universe. When we add up all the matter and energy in the cosmos, the ordinary matter that makes up stars and planets and you and me accounts for only about 5% of the total. Dark matter accounts for about another 25%, and dark energy accounts for the rest. About 70% of the universe is made of something we do not understand. This is a humbling thought. It reminds us that our knowledge is partial, that there is still so much we do not know, and that is not a failure, it is simply the truth. The universe is vast and strange and full of mystery, and we are small creatures, doing our best to understand it, with our small brains and our small instruments and our small words. And sometimes the best we can do is to say, honestly and calmly, that we do not yet know, and then to keep looking, keep wondering, keep telling the story as best we can. Now, let us bring this back to you, to this moment, to the quiet room where you are lying. You are here, on this small planet, orbiting an ordinary star, in the suburbs of an ordinary galaxy, in a universe of unimaginable scale and complexity. The light from distant stars has traveled for billions of years to reach your eyes, if you were to go outside and look up. The atoms in your body were forged in the hearts of ancient suns. The water in your cells was once rain falling on a molten earth. The oxygen in your lungs was produced by tiny bacteria living in the oceans billions of years ago. Every part of you has a history that stretches back to the beginning of time. You are not separate from the universe. You are a piece of it, a temporary gathering of its atoms, a brief flowering of its complexity. You are the universe, looking at itself, in the dark, in the quiet, at the end of a long, long story. And this moment, right now, is so improbable, so rare. Against the vast backdrop of time we have traveled through, a human life is a flicker, a single breath in the long, slow exhale of the cosmos. The dinosaurs were here for 165 million years. That is an almost incomprehensible span, and yet it is just a fraction of the time since life began. And that time is just a fraction of the time since the Earth formed. And that time is just a fraction of the time since the universe began. Your life, this moment, this quiet listening, is a tiny point on that immense timeline, but it is a point that exists. It is real, and it is here, now, in the warm dark, surrounded by the quiet echoes of all that has come before. So rest in that. Rest in the knowledge of your place in the story, not as something separate, not as an observer looking in from the outside, but as a part of it, a thread in the great fabric, a note in the long, slow song. The universe has been unfolding for 13,800,000,000 years. And you are here, at the leading edge of that unfolding, a witness to the story, a living, breathing piece of the cosmos, lying in the dark, listening, drifting. The story is not quite over. There is still the future to consider, the long, slow future of the universe, the fate of stars, the fate of our sun, the fate of all this structure we have described. But that is for the next part. For now, just be here. Just be where you are, in the Milky Way, on Earth, in the dark, in the quiet, at home in the universe, at peace in the long, slow flow of time. We have traveled a long way together. From the first instant, through the formation of atoms, through the long dark ages, through the birth of stars and galaxies, through the lives and deaths of countless suns, through the formation of our own solar system, through the emergence of life on this small rocky world, and through the rise of human beings who can look up and wonder, we have arrived at now, at this moment, at you, lying in the dark, listening. But the story does not end here. The story is still unfolding. The universe is still changing, and we can, with some care and some humility, look forward. We can follow the threads of what we know into the deep future. Not with certainty. The far future is genuinely uncertain, but we can trace the outlines, we can sketch the possibilities, and we can do so in the same calm, unhurried way we have done everything else. Let us begin with something close to home, our sun. The sun has been shining for about 4,600,000,000 years. It is middle-aged. It has about 5 billion years of fuel left in its core. 5 billion years is a very long time. It is longer than the Earth has existed, longer than life has existed, longer than the time since the first complex animals appeared. 5 billion years is a span so vast that it is hard to feel as real. And yet, it is a finite span. The sun will not shine forever. It has a life cycle, just like every other star, and we can describe in broad terms what will happen as it nears the end of that cycle. As the sun exhausts the hydrogen fuel in its core, the balance that has kept it stable for billions of years will begin to shift. The core will contract and heat up. The outer layers of the sun will expand outward, pushed by the increased heat from the contracting core. The sun will grow larger and larger. It will become what we call a red giant. A red giant is a star in its old age, swollen to enormous size, its outer layers cooled to a reddish glow. When the sun becomes a red giant, it will grow so large that it will swallow Mercury. It will swallow Venus. It may swallow Earth as well. Even if Earth is not physically swallowed, the heat from the swollen sun will be so intense that the oceans will boil away. The atmosphere will be stripped off. The surface will become a scorched, lifeless rock. The Earth, as we know it, will be gone. This sounds dramatic, but remember the time scale. This will happen about 5 billion years from now. 5 billion years. To put that in perspective, the entire history of life on Earth up to this point is about 4 billion years. We have as much time ahead of us before the sun becomes a red giant as the entire span of life's existence on Earth so far. That is an almost unimaginable amount of time. There is no urgency here, no cause for alarm. This is simply the slow, patient unfolding of a stellar life cycle. The sun, like all stars, was born, will live, and will die. And its death, when it comes, will be gentle by cosmic standards. The sun is not massive enough to explode as a supernova. After the red giant phase, it will shed its outer layers into space, forming a beautiful, glowing cloud called a planetary nebula. And at the center of that cloud, the core of the sun will remain, a small, dense, hot ball of carbon and oxygen, about the size of the Earth. This is called a white dwarf. A white dwarf is a stellar remnant. It no longer undergoes fusion. It simply shines with leftover heat, slowly cooling over billions and billions of years. The sun will become a white dwarf, and it will fade, very slowly, into the dark. That is the future of our star. But what about the wider universe? What about the stars beyond our sun? Stars will continue to form for a very long time. The universe still has vast reserves of hydrogen gas. In galaxies like the Milky Way, gas clouds will continue to collapse and form new stars for many billions of years. But not forever. The supply of gas is finite. Eventually, after perhaps 100 trillion years or so, the raw material for new stars will be exhausted. The last stars will be born, and the last stars will die. The way the universe changes after that depends on the nature of the stars that remain. The smallest stars, the red dwarfs, live for trillions of years. They burn their fuel so slowly that they will outlast every other type of star. After the last sun-like stars have died, the red dwarfs will still be shining. The universe will become a place of dim, red points of light, gradually fading as the red dwarfs exhaust their fuel one by one. And eventually, the last red dwarfs will die as well. They will become white dwarfs, like our sun, slowly cooling into the dark. At that point, the universe will be a very different place. No new stars, no shining suns, just stellar remnants, white dwarfs, neutron stars, black holes, drifting through the expanding, cooling cosmos, and even these remnants will not last forever. Over unimaginably long timescales, the white dwarfs will cool and fade, the neutron stars will spin down, the black holes will slowly evaporate through a process called Hawking radiation, losing mass bit by bit over trillions upon trillions of years. The universe will become darker, colder, emptier. This is sometimes called the heat death of the universe, a final, quiet state where nothing much happens anymore. Just a thin, cold, endless emptiness, with the last remnants of stars and galaxies scattered so far apart by the expansion of space that they can no longer see each other. But we must pause here and say something important. All of this description of the far future is based on our current understanding, and that understanding is incomplete. The fate of the universe, on the very longest timescales, is genuinely uncertain among scientists. It depends on the nature of dark energy, which we do not understand. If dark energy remains constant, the expansion will continue to accelerate, and the universe will end in a cold, empty state. But what if dark energy changes over time? What if it weakens, or reverses, or does something else entirely? We do not know. There are other possibilities. The expansion could eventually slow down and reverse, leading to a collapse. The universe could end in a big crunch, the opposite of the Big Bang. Or something else could happen, something we have not yet imagined, based on physics we have not yet discovered. The honest answer is that we do not know the ultimate fate of the universe. The not knowing is with us here, at the end of the story, just as it was at the beginning, and that is all right. We can hold the future lightly. We can acknowledge the uncertainty. We can rest in it. What we can say with more confidence is that the near future, the next few billion years, is relatively well understood. The sun will become a red giant. The Milky Way will merge with Andromeda. The two galaxies, which are currently approaching each other at about 250,000 miles per hour, will swing through each other in a slow, spiraling dance. Their stars will mingle, their shapes will distort, and eventually, over a few billion years, they will settle into a single, larger galaxy. Some have called this future merged galaxy Milkdromeda, but the name is not important. What matters is the simple fact. Our galaxy, our home in the universe, will change. It will merge with its neighbor, and the night sky, for any beings alive to see it, will look very different than it does today. But all of this is so far in the future that it should not trouble your sleep. These are thoughts to drift on, not to worry about. The universe is slow. The universe is patient. The changes we are describing happen on timescales of billions and trillions of years. Against that backdrop, a human life is a flicker, a single breath, and that is not a sad thought. It is a peaceful one. It means that the vast, slow processes of the cosmos will carry on long after we are gone, and we are part of them. For this brief moment, we are here, now, at this particular point in the long history. We get to see the universe in its middle age, when stars are shining, when galaxies are bright, when life has had time to evolve and look up and wonder. We are living in the springtime of the cosmos, and that is a gift. So let the future unspool in your mind like a long, slow ribbon. Stars being born, stars dying, galaxies merging, the sun swelling into a red giant, the Milky Way and Andromeda dancing together in the dark, the last stars fading, the universe growing colder and emptier. Or perhaps not, perhaps something else. The uncertainty is part of the calm. We do not need to know the ending. The story is not about the ending. It is about the unfolding, the long, slow, patient unfolding, from the first instant to now, and from now into whatever comes next. The universe is still expanding. The story is still being told. And you are here, a part of it, drifting in the quiet dark, listening to the slow pulse of time. The future is vast and soft and full of mystery, and that is a gentle place to rest, a gentle place to let your mind settle as the words grow slower and the night grows deeper and sleep comes closer. The story is almost done. Just one more section, one more soft step, and then the dark, and then the stillness, and then sleep. And now we have arrived at the final part of our story, the last soft chapter, the quiet close. There are no new facts to learn now, no new names to remember, no new places to visit. There is only the gentle settling of the story into stillness, like a wave that has traveled a long way across a vast ocean, and now, at last, reaches the shore. It slows, it softens, it spreads out thin and quiet across the sand, and then it is still. Let us remember, just for a moment, how this story began. Or rather, let us remember that we do not know how it began. We stood together at the edge of knowledge, looking back into the dark before the first instant. We acknowledged that what came before the universe is not known. It may not even be a meaningful question. Time itself may have started with the universe. And that mystery, that honest not knowing, was not a gap to paper over. It was the frame around the story, the soft, dark edge that held the picture. We stood there together, and we breathed, and we did not try to solve it. We let it be what it was. A mystery, a quiet boundary. The place where the known meets the unknown, not with a clash, but with a gentle, peaceful acceptance. And then, from that edge, we stepped forward, into the heat, into the density, into the first fraction of a second. From that first instant, the universe began to expand and cool. It was unimaginably hot and dense and small, smaller than an atom, hotter than anything we can truly picture. And then it began to stretch. Not an explosion in space, but an expansion of space itself. The stretching has never stopped. It is still happening now, even as you lie here, even as you breathe slowly in the dark. The universe is expanding. Galaxies are moving apart. Space itself is growing, creating more room where there was less room before. And that expansion, that cooling, has been the deep engine of the whole story. Because cooling allows structure. Heat is the enemy of form. When things are too hot, they fly apart. They cannot stick together. They cannot bind into larger wholes. It is only as the temperature falls that new kinds of order become possible. This was the quiet rhythm we followed through every chapter. Cooling and structure, stretching and cooling. As space grew, the heat spread out, became thinner, became gentler. And in that growing gentleness, new things became possible. First, the smallest particles, the quarks and electrons, flickered into being out of the formless energy. They swam freely in the hot, dense soup, colliding and bouncing, too hot to bind. Then, as the temperature dropped, they joined together into protons and neutrons. The first small, stable specks of matter, then those protons and neutrons combined into the first simple atomic cores, mostly hydrogen and helium, in the first few minutes of the universe's life. A brief, intense burst of building, and then the window closed. The universe was left with a specific mix, mostly hydrogen, some helium, a trace of lithium, and nothing heavier. No carbon, no oxygen, no iron. Those would come later. They would need stars. Then, after 380,000 years, the universe was cool enough for electrons to join those cores and form the first complete whole atoms. And at that moment, the light was set free. The photons that had been trapped in the hot fog, bouncing endlessly from electron to electron, were suddenly released. They streamed out in all directions, moving in straight lines at last. The universe became transparent. And those photons, that first light, is still traveling today. We can still detect it. It is called the cosmic microwave background, the faint leftover glow from the moment atoms were born, the oldest light in the universe, a quiet whisper from the edge of time. And then came the long dark, the cosmic dark ages. Hundreds of millions of years with no stars, no new light, just a vast, dark ocean of hydrogen and helium gas, with the faint glow of the cosmic microwave background slowly fading as the universe continued to expand. It was a time of deep stillness, a time of waiting, but within that stillness, something was working. Gravity. Patient, quiet, relentless gravity. It pulled the gas together, slowly, gently, over tens of millions of years. The slightly denser regions became denser still. The gas gathered into filaments and clumps. The universe was developing structure, invisible and silent in the dark. This was the quietest part of the whole story, the most peaceful part, the part where nothing seemed to be happening, and yet everything was being prepared. Like a field lying fallow under winter snow, like a breath held before a long exhale. The Dark Ages were a long, slow, patient gathering of forces, and we lingered there, in that quiet, because it is a good place to rest, a good place to drift, a good place to let the mind soften and the breath slow. Then the first stars ignited, the first light bloomed in the dark, the cosmic dawn. After hundreds of millions of years of darkness, points of light began to appear. One by one, in the densest cores of the collapsing gas clouds, the temperature and pressure reached the critical point. Fusion began. Hydrogen fused into helium. Energy was released. The stars turned on. Those first stars were born from almost perfectly pure hydrogen and helium. They were different from the stars we see today. They were, we believe, enormous. Hundreds of times the mass of our sun. They lived fast and died young, burning through their fuel in only a few million years. And when they died in enormous explosions, supernovae that scattered their newly forged heavy elements into space. Carbon, oxygen, nitrogen, iron, all the elements that would later form planets and oceans and living bodies. The first stars were the pioneers. They broke the darkness. They seeded the cosmos. And then they passed the torch to the generations that came after. Gravity continued its work, pulling stars together into galaxies. Our own galaxy, the Milky Way, began to form in this era. It grew by gathering gas and merging with smaller galaxies. The invisible scaffolding of dark matter, whatever it is, helped shape it. Galaxies gathered into clusters, and clusters into superclusters. The cosmic web, that vast, sponge-like structure of filaments and voids, became illuminated with the light of stars. The universe was no longer dark. It was bright and complex and busy. And within one of those galaxies, in one of its spiral arms, in a quiet suburb far from the center, a particular cloud of gas and dust began to collapse. It was about 4,600,000,000 years ago. The cloud was enriched with the ashes of earlier stars. It contained hydrogen and helium, but also carbon and oxygen and iron and all the rest, the raw materials for building planets and for building life. The cloud collapsed. It spun into a disk. At the center, a protostar grew, gathering mass, heating up. When the core reached 10 million degrees, fusion ignited. The sun was born. Around it, the disk of leftover material began to clump together. Dust grains stuck to dust grains. Pebbles formed, boulders formed. Planetesimals collided and merged. Over millions of years, the planets took shape. Rocky worlds close to the sun, gas giants farther out. One of those rocky worlds was Earth. At first it was hot and molten, bombarded by leftover debris. A Mars-sized object struck it a glancing blow, and the debris from that collision coalesced into the moon. Slowly, the bombardment eased. The Earth cooled. A thin crust formed. Volcanoes poured out gases, building an atmosphere. Water vapor condensed and fell as rain. Torrential, endless rain, for millions of years. The oceans formed. The Earth became a water world, warm and shallow and rich with dissolved minerals. And then, in those oceans, something happened that we still do not fully understand. Life appeared. Simple at first, single cells, tiny sacs of organic molecules, capable of taking in nutrients and dividing. We know life was present very early, within about 1 billion years of Earth's formation. But exactly how it began, the specific steps from non-living chemistry to the first living cell, is still a mystery. It is genuinely unresolved, and we can let that mystery be what it is. We can sit with it calmly, without needing to solve it. The not knowing is woven into the story, as it has been from the very beginning. For more than 2 billion years, life remained simple. Single cells floating in the oceans, forming mats and mounds. Some of them learned to capture sunlight, to do photosynthesis. They produced oxygen as a byproduct. Slowly, over hundreds of millions of years, oxygen built up in the atmosphere. It changed the chemistry of the planet. It allowed new forms of life to evolve. Cells learned to cooperate, clustering together into multicellular organisms. Animals appeared. Plants appeared, life moved from the oceans to the land. It diversified and spread, filling every niche, adapting to every environment. There were setbacks, mass extinctions. The worst of them, about 250 million years ago, wiped out most life on Earth. But life recovered. It always recovered. It was patient. It had time. Dinosaurs rose and dominated the land for 165 million years. Then an asteroid struck, and they were gone. And from the ashes the mammals rose. They had been small, scurrying creatures, living in the shadows. Now they diversified and spread. Among them, a branch developed larger brains, complex social structures, hands that could grasp and shape tools. They developed language. They looked up at the night sky and began to wonder. They began to tell stories. They became us. And here we are, at the end of this long chain of events, at the leading edge of nearly 14 billion years of unfolding. You, lying in the dark, a living, breathing piece of the cosmos. The atoms in your body were forged in ancient stars. The iron in your blood was made in a supernova. The oxygen in your lungs was produced by tiny bacteria billions of years ago. The water in your cells fell as rain on a young molten earth and has been cycling through oceans and clouds and rivers and living bodies ever since. Every part of you has a history that stretches back to the beginning. You are not separate from the universe. You are not an observer looking in from the outside. You are a part of it, a temporary gathering of stardust, a brief flowering of complexity. The universe, looking at itself in the quiet dark, wondering at its own existence. Against the scale of the story we have told, this moment is so small, so brief. 13 billion, 800 million years of unfolding, and here you are, in this one flicker of time. The entire history of human civilization is a blink compared to the Dark Ages. The dinosaurs were here for a span so vast that it makes our time on Earth seem like a single breath. And even the dinosaurs were latecomers to the story. Life had been here for billions of years before them, and the Earth had been here for billions of years before life. And the universe had been here for billions of years before the Earth. And all of that vast, slow, patient unfolding has led to this, to this quiet room, to this breath, to this heartbeat, to this listening in the dark. It is a rare thing, this moment, a precious thing. Not because it is grand or important in some cosmic sense, but simply because it is, because it happened, because all of those events, from the first instant to the first atom, to the first star, to the first cell, to the first thought, led to this, to you. The universe has done something remarkable. It has become aware of itself. Through you, through all of us, the cosmos can look back at its own history. It can tell its own story. It can wonder at its own beauty. And you are part of that. You are the universe, telling itself a story, in the dark, in the quiet, as you drift towards sleep. And now the story is done. It has been told, it has been spoken into the quiet, and it has settled into the air, and now it is time to let it go. You do not need to remember it. You do not need to hold on to any part of it. The story was never meant to be a lesson. It was never meant to be memorized or repeated. It was meant to be a companion, a soft voice in the dark, keeping you company while you drifted towards sleep. If you remember nothing of it, that is all right. If you fell asleep halfway through and missed the ending, that is all right too. The story has done its work simply by being here, by filling the silence, by giving your mind something slow and gentle to rest on, by reminding you, in a quiet way, that you belong to something vast and old and beautiful, that you are part of a story much larger than yourself, and that you are safe in that story, held by it, carried by it, like a leaf floating on a slow, wide river. Let the words begin to slow now. Let the sentences grow shorter. Let the pauses between them grow longer. There is no more ground to cover, no more thresholds to cross, no more epochs to describe, just the quiet settling of the story into stillness. Like a light fading slowly, like the last ember of a fire, glowing soft and red, and then dimming, and then going dark. Like the surface of a pond, after a stone has been dropped in, the stone sinks, the ripples spread out and out and out, growing fainter and fainter, wider and wider. The water shimmers, the reflection of the sky trembles, and then, slowly, the ripples fade. The surface becomes smooth again, still again, dark again. The pond holds the memory of the stone, somewhere deep in its quiet depths, but the surface is at peace. You are here. You are safe. You are warm. The bed holds you. The blankets cover you. The dark surrounds you, soft and familiar. Outside, the stars are shining, whether you can see them or not. The Milky Way is arcing across the sky. Andromeda is out there, 2.5 million light-years away, drifting slowly toward us. The universe is expanding, stretching, cooling, as it has been for almost 14 billion years, and you are a part of it, a small, precious, irreplaceable part of it. The atoms in your body have traveled a long, long way to be here. They have been through stars, through oceans, through the hearts of ancient living things, and now, for this brief moment, they are you. They are gathered together in this shape, in this consciousness, in this quiet awareness, and soon they will drift apart again. They will return to the world. They will become soil and air and water. They will be taken up by plants. They will become part of other living things. The cycle will continue, as it has for billions of years, and that is not a sad thought. It is a peaceful one. It is the same peace we felt in the dark ages, the same peace we felt in the long, slow gathering of gas clouds, the same peace we felt in the patient work of gravity. Everything is connected, everything is part of the same story, and the story does not end, it only changes, it only unfolds, it only continues, in one form or another, for as long as the universe exists. So let yourself drift now. Let yourself sink into the quiet, into the dark, into the stillness. The story has been told. The journey is complete. The arc of nearly 14 billion years has been traced, from the first instant to now, from the heat to the cooling, from the plasma to the atoms, from the dark ages to the first stars, from the galaxies to the solar system, from the young Earth to the first life, from the single cell to the human mind. All of it has led here, to this moment, to this breath, to this quiet listening in the dark. And there is nothing more to add, nothing more to explain, only this: the slow, steady rhythm of your own breath, in and out, in and out. The soft weight of your body against the bed, the gentle darkness behind your closed eyes, the fading echo of a voice that has been telling you a story, a long, slow story, a story that is now complete. Sleep is coming. It is very close now. You can feel it at the edges of your awareness. A soft tide, rising slowly. A warm fog, rolling in from the sea. Let it come. Do not resist it. Do not try to stay awake to hear the end of the words. The words are ending. They are growing softer and slower and fewer. Soon there will be only silence, only the quiet, only the dark, and you, drifting in that dark, safe and warm and at peace. The universe has been unfolding for a very long time, and it will continue to unfold for a very long time after this moment has passed. But you do not need to think about that now. You do not need to think about anything at all. Just breathe, just drift, just let go. The story is over. The night is quiet, the dark is soft, and sleep is here. Sleep is here now. Close your eyes. Let the last of the words slip away, into the quiet, into the dark, into sleep.